Okay, I welcome the participants to this one-day online workshop on understanding the science behind geological hazards for early warning and mitigation. Throughout the day, we have planned to have four important lectures catering to different fields of different niche areas of geological hazards, and what are the advanced way to forecast to give early warning and mitigation. We will discuss in detail about this. So this one day online workshop is being conducted by the IRS distance learning program. We are all a part of that. It basically aims at providing the integrated and multidisciplinary perspective on major geological hazards and what contemporary approaches we can adopt to mitigate this for risk reduction as such. Geological hazards like, as you know, earthquake, like landslide, land subsidence, cryospheric hazards that wreaks and havoc for quite some time in the mountainous areas in Dehradun, we are situated presently. Particularly, it is dangerous in tectonically fragile or environmentally fragile regions like this. The workshop begins with an overview of geological hazard that will be covered immediately after this welcome session by Dr. R.S. Chatterjee sir, Group Director, GDM Group, and followed by one lecture by myself that will be on the rainfall threshold and modern techniques to cater to the landslide early warning system development, etc. That will be covered by me, followed by one lecture on the cryospheric hazard by Dr. Pratima Pandey, and another one we have in dealing with your earthquake or seismic hazards and some geological instruments. So because the faculty is not available today, so we'll have to reschedule slightly a bit about this particular lecture. And obviously, it will be covered, it will be catered to, but may not be by the same faculty as it has been mentioned in your schedule. So in brief, the workshop also covers the advances of all these four domains of hazard, as I have told you. And overall, it aims to enhance the participants' understanding about the state of the art technology and about the observation tools, what cues we can take from remote sensing and satellite image, modeling techniques, advanced modeling techniques, and early warning frameworks, development of early warning frameworks, obviously, just to enable them to appreciate the scientific basis of understanding of geological hazards and mitigation in the context of sustainability and mitigation of disasters as such. So thank you. I next request Dr. R.S. Chatterjee sir to say a few words about this as introduction, and I request him to continue with his lecture immediately after this. Over to you, sir. Thank you.
Yeah. Thank you, Dr. Shobhan. So the first thing is the participants. What are this level of participants? Can you please tell, and what are the participation from how many participants are there? That is okay. Maybe our distance learning department know about that, but whether they all know remote sensing, or all are from geology background, I don't think they are not from geology background all, isn't it? But
Yes,
whether they all know remote sensing, that also, I think it is not restricted, because the topic is so general topic and so relevant and so important for everybody that we do not want to restrict that way. So that is the reason. Maybe all of you may not be a specialist in the area of remote sensing, or may not be this your very seasoned geologist. Maybe you have uh, some idea about geology and geological this your phenomena or processes. So that is the reason maybe we in the overview lecture we have uh, kept here that where we'll discuss about the introductory these areas so that even the common man understand how remote sensing, how geology is important. And finally, we'll discuss about the this your geological hazards, because there are many other natural hazards, but we'll focus on geological hazards in this particular workshop. But that does not mean other hazards are not important or they are not dangerous. They are also equally dangerous, like hydrometeorological hazards, like floods and this your drought and many others. Similarly, climatological or environmental hazards. Some hazards you cannot separate individually as a environmental or climatological, but it is also at the same time geological. So those things we will discuss here in this workshop. So as already Dr. Shobhan has very nicely elaborated what exactly we are going to focus in this workshop, and understanding the science and what are the mitigation measures, what are the present state of knowledge in the area of remote sensing, and how geological phenomena can be addressed, particularly using from remote sensing these your techniques, remote sensing data analysis, and along with that, in situ observations, geodetic observations, like your GNSS or GPS observations, then the interferometrics are, and many other techniques of geodetic, these your observations and measurements, and geophysical as well. So we'll focus on many areas, and in fact, it is a multidisciplinary integrated approach. What is the need of the day? But this predominantly, what is the role of remote sensing? That is what we are going to tell. Okay, so I will not extend further about the workshop, this your overview. Now I will focus on the overview of the first this your session, that is overview of the geological hazards and how remote sensing is going to help. Okay, so let us start now our first session, uh, and I am going to do that. So this is remote sensing of geological hazards. Uh, I think it is coming to everybody. Ashok ji can confirm. Ashok ji, it is shared to all the participants.
Yeah, it's fine, sir.
It is fine.
Yeah.
Okay, so good.
Yeah.
So very good. So this is remote sensing of geological hazards and overview. And I am Dr. R.S. Chatterjee, so from Geosciences Department of Indian Institute of Remote Sensing. So see, just to begin with the remote sensing as geology, isn't it? So first, many of you know very well what is remote sensing and how it is being used in geosciences. But even then, there may be some participants, they are very new to the area of remote sensing. There are some participants are not very seasoned in the area of in the geological the processes and phenomena. Their understanding may be introductory level. So I'll also discuss how what is remote sensing, how remote sensing can be used for this your geological feature identification, and for understanding the geological processes and geological phenomena. So remote sensing as a definition, you can see here, this is a very standard definition, that it is the science of sensing Earth and nowadays also planetary objects. Okay, so it is sensing Earth and planetary objects from a remote distance without coming in contact with the object. But it is very important that using electromagnetic radiation. So using electromagnetic radiation which is coming from this object, okay, that receiving that electromagnetic radiation from the satellite or from the spacecraft, from the aircraft, and also from the drone, okay, we can infer about the properties of the objects. So that is what is known as remote sensing. Now, you see in the area of geosciences, there are many applications, but there are three basic applications. What I have made it the blue, that lithological this identification, that is the rock types, Then the geomorphological mapping, this is the landforms or the what is the shape of the earth surface, okay, in terms of your elevation, slope, and this ruggedness, as well as the material content. And then the geological structures, I mean to say that these your tectonic structures, those are formed due to the crustal deformation, okay. And there are many other applications that I have made it this your subdued, no, in the light gray color, because this is not the this your requirement for this particular this session. And what is important for today is the geological hazards mapping and monitoring, as well as mitigation and early warning. So there are many more things. But here you see remote sensing alone is not 100% sufficient. Okay, so we need to use it in with complementary with other data sets or in synergy with other data sets. Most important is the geophysical data and geodetic observations. Okay, so for this particular purpose, so geophysical, this your observations, geodetic observations, subsurface geology sometimes is very, very important. Sometimes we can infer indirectly from geophysics. Okay, sometimes we can get it directly by trenching, okay, by drilling, and ground truths. Okay, so these are all together we can do better on the geological hazards. Now, you see, just to begin with, introductory, that how these rock types are identified. I'm not going to the details. What is the specific rock type you can identify? Okay, but just for a beginner, we need to know how a by remote sensing can identify whether it is a broadly igneous rock or it is a broadly sedimentary rock or a broadly metamorphic rock. Okay, for this purpose, just you uh, just note down these particular characteristics. Very, very the standard characteristics of the igneous rocks. This is crystalline rocks. What is important? Igneous rocks, they are formed from the melt by crystallization. So they are crystalline rocks. So here the grains are interlocked. So that is the reason it is homogeneous, massive, hard, and compact, and very highly resistant. And in general, they do not have any layering. Definitely, they do not have any bedding because they are not deposited rocks. So they are crystallized rocks. And for the this is uh, coarser grained rocks, particularly this texture is very finer grained, extrusive rocks like lavas and these things. Sometimes it is fine. Okay, so what these are the characteristics what from which we can infer over the image from the aerial photograph that whether it is igneous rock, it is metamorphic rock, or sedimentary rock. On the other hand, sedimentary rocks are very soft, they are bedded, and they are basically deposited rocks, so they are very easily erosible because they are soft and very, very easy to dissect sedimentary rocks. They are because they are soft, vulnerable to dissection, so there are many drainage develops. Okay, and because they are layered rocks in general, so there will be some typically there will be different kind of landforms in general, ridge and valley, but not always ridge and valley. So the layered appearance you will find. So that is what is important. Okay, and metamorphic rocks, because there is due to high temperature and pressure, it got deformed, it got recrystallized. So there is this stress applied over the rocks. So that is the reason these mineral grains, they're aligned in a particular directions. Some weak planes developed, and these weak planes become parallel to each other. And these are the foliation planes. So all along these weak planes, there are preferential weathering and erosion happen. Okay, and that is the reason they look like striated this appearance over the rock surface. So now you see all these characteristics. This your separately, if you analyze, and in this particular sample, you have all three rocks: igneous, metamorphic, and sedimentary rocks. Now you see that this upper part, it is very, very this your characteristics of the sedimentary rocks because it is very soft, it is a layered appearance, there are a lot of drainage, and their surface is very smooth because they are easily weathered. It can be easily weathered by the these physical processes like by the running water or by the wind. Okay, so this is sedimentary rocks, whereas in the central part, this is igneous rocks. As I have told you these characteristics, so you can just compare and you can find out. So this is a massive, this is hard and compact appearance here is there, and the texture is very, very coarse. Whereas in the lower part, there are the foliation plains, okay, that gives you the preferential weathering, and the striations are very, very important. Sometimes in metamorphic rocks, you will find these deformational structures like folds, like your faults, okay, like shearing, okay, many more. Okay, so in the next slide, you can see some more examples. I will not elaborate because our purpose of today's session is geological hazards, so I will not go much details on that. Just to briefly tell you how these rock types can be identified. Like here, you can see these are very easily you can identify they are the volcanic rocks, isn't it? The volcanic cones you can see, there are lavas, plateau you can see, isn't it? There are pyroclastic you can see. Whereas here you can see there are two rocks. They are very close to each other, but they are not the same. Here, this one, for example, it is an igneous rock, whereas these foliation plains are very, very prominent, isn't it? So this is basically the metamorphic rock. These two also, along with these foliation plains, there are the structures are also prominent. This is the folded structure. So these are metamorphic rocks. You can very easily identify. Whereas these two here, okay, you see here their surface is so smooth. There are a lot of drainage. That means there are high level of dissections, and the surface is quite smooth. And this layered appearance of the this rock is very, very prominent on the image. So these are basically the sedimentary rocks. So based on this very broad this criteria, you can identify igneous, metamorphic, and sedimentary rocks. Okay. Now, the geomorphology, one of the basic requirement for even for geological hazards or any applications in geosciences, you need to know about the geomorphology of this area. What are the rock types, like lithology of the area, and if there is any geological structures occurring in this area. That means any kind of deformation has happened in the past or not. So now in this particular slide, we are discussing about the geomorphology. So geomorphology, basically it deals with the physical processes in shaping the earth surface, okay? In shaping the earth surface as a function of its elevation, slope, and surface ruggedness. At the same time, what is the range of material your content? Means this grain size of the materials is very important, whether it is finer these particles or coarser particles, whether it is well sorted or it is a mixed your grains, both coarse, both fine, mixed all together, jumbled up, or it is very, very sorted, only the coarse or only the fine grains. So these are very, very important. This all tells about what is the geomorphic processes operated. And the shape of the earth surface is basically governed by the elevation, slope, and the surface ruggedness. And the unit of the geomorphological study is a landform. Okay. So, and the landform is characterized by unique topography and this material composition, and if this shape and this structure of this object. Okay. So see, I'm not going to much details about geomorphology. Here you see the example what it is given here. You can see here your shape is very, very important for this particular object, isn't it? And you can see there are some sloping this surface, and you can interpret that this is basically alluvial fan. In fact, this is the Ghaggar River fan, and over which this Panchkula city. So this is the Panchkula city has been developed. This is the habitation of Panchkula city here, and just nearby is Chandigarh, and then the south of Chandigarh is this Mohali. Okay, so this is how geomorphology you can interpret. Now you understand this Panchkula city here. You can see that it is over the alluvial fan, where the rocks are very, very loose, unconsolidated, isn't it? And here it is also sloping terrain. So these are not highly stable land. So one need to be careful on that, because if there is a seismic, seismicity happens or earthquake happens of a moderate to high magnitude. So here there is the peak ground acceleration will be quite high. So this type of information you can interpret beforehand if you have the geomorphological knowledge with you. Okay. Now there are a number of examples I have shown just for your better your understanding. So here all are fluvial geomorphology. Like you can see here, this the floodplain, then active floodplain, older floodplain, then the alluvial plain. Okay, there are a number of these landforms. Okay, like the levees, natural levees. I mean, these old natural levees, then oxbolex. Okay, I'm not going to the details now. Here, for example, you can see here the river terraces, and river terraces means there are some kind of active tectonics because where the river was flowing, okay, because of some tectonics, some this your terrain, this your upliftment or the displacement. So the southern part of this area has gone down. Okay, that is the reason there is the river needs to incise deeper. Okay, so the active floodplain becomes the older floodplain, and finally it is preserved as a the terrace, and this is the river terrace. And you see, this is not just one level of river terrace, but one, two, three, four. Okay, so there are at least four the river terraces exist here. So each of these river terrace represents there was some this tectonics happened, some kind of offset of the this fault has this work in this area, and that causes these terraces to develop. So these are the records of the this your past seismicity, isn't it? So now see here, this is the anomalous this pattern of the stream, and here you can see the meander scar and meander scroll, their abundant channel and alluvial plain, many more things. Paleo channel belt between the Kanpur and Lucknow. So this is just for example how you can interpret the these different landforms, which is very important for geomorphological understanding of the area. Now for geological structures, these are basically developed due to the this tectonics. So these are the deformational structures like folds, faults, lineaments. Lineaments means joints and fractures and unconformities. Just for example, if you see the folds, these are most important geological structures when it is exposed. So then remote sensing is very important because it gives you the synoptic view of the folded structures, and you can interpret the geometry of the folded structures. Like here you can see the fold. Here this folded bed is dipping relatively gentler, whereas if you go proceed this direction, this dip of the folded bed is it becomes steeper and steeper, and when you are reaching to this end, this folded bed becomes almost vertical. It is a subvertical folded bed, isn't it? And basically it is an inverted this your fold, and it is a dome like structure. Whereas here you can see this is a plunging this your anticline, and here you see there is a fault because offset of the these two blocks. This block has gone this down, this has gone up. In fact, this is the Jamuna tear fault. This is a Strikesly fault, but it is not the simple Strikesly fault. This is a Strikesly fault which has offset this thrust sheet. Okay, the thrust sheet has been offset here, and basically it is the Himalayan frontal thrust. Here the boundary is the Himalayan frontal thrust. The Himalayan frontal thrust has been offset, and the thrust sheet has been this offset by this Strikesly fault, and this is why it is known as this tear fault. Now here you can see there are faults, there are fractures, and there are some of the weak planes. They are very regular in pattern, and so these are the joint planes. Okay. Now coming to the geological hazards, this is our session exactly. So you see these geological hazards are naturally occurring and are anthropogenically induced hazards of geological origins. They are the geological hazards. Although natural hazards can be grouped into three types, as I told you in the introductory statements, that geological, hydrometeorological, and environmental or climatic hazards. Now, under geological hazards, uh, they can be caused by the internal geological processes or external geological processes. External geological processes, and these kind of hazards are known as exogenous, and the geomorphic processes is known as the exogenetic or exogenous geomorphic processes, like mass movements, for example, landslides, like avalanches, like rock falls. So these are all governed by the gravitational forces. It is by the force of gravity. Whereas endogenous, here the source energy, it comes from inside the earth, like earthquakes, like volcanoes, like the tsunamis. Here the source energy is from the earthquake, and this earthquake energy comes from inside the earth. It's not later on after this happens, earthquake happens, gravity operates. But at the beginning, gravity is not responsible. But whereas in exogenetic processes, in all the cases, you just look into that. These are all governed by the force of gravity. Now, you see geological hazards of anthropogenic origin. For example, there are mining hazards like coal fire, the mine subsidence, roof collapse, groundwater hazards like groundwater depletion induced this aquifer system compaction, and that causes land subsidence. Sometimes groundwater pollution is also one of the very this your serious geological hazards like arsenic contamination and the fluoride contamination. Okay, so these are uh, uh, to a great extent is a man-made, but there are certain this water pollution also caused naturally. Okay, that source is from the nature itself. Now you see in the landslide hazards, there is a this your dedicated lecture on landslide. So I will not discuss landslide much here. So only see this is the classification of landslide based on the type of the movements. There are 5 types of broadly 5 types of movements are classified like falls, topple, slide, spread, and flow, and the nature of the materials like bedrock or it is the coarse this your particles like the gravel or debris. Okay, based on that, these landslides are classified, and the finally the another material this material content is the those are the very fine grained like soil or earth. Okay, this is known as. So based on that, this combination of these three material types and 5 movements. So this many this mass wasting processes can be classified. Okay, mass movements can be classified. So, but broadly, they are all known as the landslide. But actually, there are landslides where it is sliding, but this when it is spreading. So this is not a slide, but it is a spread or it is a flow or flow. So in case of finer grains, this flow or spread are more important. In case of this debris, there is the spread and sometimes slide happens. But in case of rocks, there is falls, topples, and slides are important, isn't it? And there are all the illustration. And the next session, it will be discussed more. So I am not going to discuss on that. Just a few things I will tell you, just overview. See how remote sensing can be used to identify this landslide scar, isn't it? So here you see this is very old photograph. Okay, so from this photograph and from this image, in the history image, we can see that here the landslide movements are essentially by a translational movement where the slip surface is planar. Whereas if you see here in this particular, see it, this scar looks like a spoon, isn't it? So, and on the image also, you see here. So here what it tells you, this is the slip surface is curved. So here the nature of the landslide movement is rotational in nature. So this is categorized as the rotational landslide. Now nowadays, this your landslide scar identification is very important. Or landslide inventory is very important to understand how far this area is vulnerable to landslide or susceptible to landslide, isn't it? So in general, what traditionally we used to do it is by visual interpretation of high resolution images. But then there are some these your advanced techniques like image segmentation. Then there is a change detection before and after the landslide. Okay, but nowadays what people are using, what is latest is this by AIML based algorithm. Okay, so here this maybe algorithm, maybe image segmentation, but the process is the artificial intelligence. Okay, so by this you have different kind of algorithms you can adopt. For example, in this case, this convolutional neural network CNN algorithm is applied, where the different combinations or different of kernel sizes has applied, and based on that, this landslide scar can be very easily identified by automated manner, isn't it? This is just an example that IRS has been doing from decades in the area of landslide hazard zonation or landslide susceptibility mapping. For example, you see here, this is one of the area like your Uttarkasi in Uttarakhand area, Uttarkasi area, you see before 2003, there was no landslide in this area, or there are very small scar you can find out. But after this 2003, you see there are the major landslide happened. Okay, the Barnabat landslide, isn't it? So this is the area we studied before. Okay, by ISRO. and we identified this area is highly susceptible zone. And this kind atlas was published from ISRO in 2001. You see, in 2003 there is a massive landslide. So that means, see, this, if you make this area that identify the area is highly susceptible, there is a high chance of having landslide. But it does not mean that all the high susceptible area will be this affected by landslide immediately. Okay, because there are some triggering factors are very, very important, and that is where the rainfall is very, very important. How much rainfall has happened, what is the duration of the rainfall, what is the intensity of the rainfall or the critical rainfall. So those things are very, very important. That will be again discussed in the next session. And sometimes the earthquakes, this is seismically induced landslide. Okay, so here you see this, after this landslide happened, again we work in this your these results or the layers what you have generated is 1:25,000 scale, but here it is 1:5 to 10,000 scale. So that is much more finer resolution. For that purpose, you need very high resolution to very high resolution images. Okay, or nowadays you have image even up to 30 centimeter from ISRO. This your satellite images. 30 centimeter is the size of the pixel for spatial resolution. Okay, so that means it is much less than a meter spatial resolution. So you can do with this kind of spatial resolution, you can do even up to some 1:5,000 or even less. Okay, even larger scale this mapping you can do. Now you see, in case of landslide, this for early warning, one of the important thing is by modeling, that is the rainfall threshold or this seismically induced landslide. So, okay, most importantly the rainfall threshold, but whether there is some slow movement or creeping movement is happening before the major sliding is going to occur. So that can be this picked up, that can be identified by the advanced geodetic techniques like differential interferometric SAR. This is one of the pioneering studies in the 1990s. It was published. So you can see the slow movements is the color, this cycle, or this is in the technical terms, these are known as the fringes. That represents 2 pi radian phase difference between the two synthetic aperture radar microwave images. That is for a particular duration. So for a particular duration, if you take 2 images and this for this duration, how much this land surface has been moved, that is very slow movement. It can detect in the on the level of it is in millimeters. So that is what you can see here. Each phase cycle is only 2.8 centimeters. Okay, 2.8 centimeter movements you can detect here. So for example, here only there are the 2 phase cycles. So it is not more than 5 centimeter movements you are able to detect. So this is one of the this your upcoming area where you can this identify, you can detect the slow movements before the major landslide is going to happen. Like in case of this Terry Dam, we have been working for decades, at least for 2 decades. Okay, and in case of Nainital area also, this there are some landslides. Okay, so that also you can identify these movements. So from these movements you can see this is the this your subsidence. Red color is the subsidence movement. So that means it's going down the slope. Okay, so those kind of movements you can identify. Okay, it's in some area it is showing this is opposite to the slope. That is why it is a blue color. It does not mean it is uplifting, but it is the movement is opposite in the opposite direction with respect to the satellite orbit. Okay. Now see for earthquake hazards. So what is an earthquake? This earthquake is another important geological hazard. So earthquake is caused by a sudden rupture of the earth crust, isn't it? And here you see this is the elastic rebound theory has been illustrated here. Why? Because this is one of the explanation how earthquake occurs. Okay, and how this elastic rebound theory explains earthquake. See here we have this described. The rocks initially bent until the strength of the rock is exceeded. So you can see here rock is bending. Okay, because there is the stress is applied into 2 directions, shearing stress. Now see it is first it is this deformation or bending happens. Here is the maximum limit of the bending. Then there is this rupture happens. Okay, here the beginning of the rupture. Here there is no rupture, but here you can see the rupture where the fence, what it was your placed here. Here you see the fence is bent, but here you see fence is separated, offset, and these blocks as well. And here, after some time or immediately so these two blocks which got bent, okay, so they come back to the original shape. Okay, so this is quickly rebound to an undeformed shape, isn't it? And due to this offset or displacement of these two blocks, the energy is released, and this energy is released in terms of waves, and these are the seismic waves. And these seismic waves can be detected by the seismometer. That is the instrument used to detect these seismic waves. There are different types of seismic waves like P waves, S wave, primary wave, secondary wave, and the surface waves. But the surface waves, they are the these destructive forces, and that causes the damages of the this over the Earth's surface. Okay. Now see this as far as the advanced technologies is concerned. Again, I am coming back to this radar interferometry. You see, this is the pioneering study of this synthetic aperture radar interferometry published in 1993. Here, this Landers earthquake with a magnitude of 7.3. It was shown due to this earthquake how much this deformation of the Earth's surface has happened. Okay, and this here each phase cycle or each coloring represents 2.8 centimeter or 28 millimeter. You see the white lines. This represents this rupture, but this is the faults. Okay, and this is the model diagram. And here this is another example. Here you see this part is showing these fringes. These are the closed fringes. In fact, and this fringes represents that the surface is going down. Okay, so this part has gone down and this part remains intact. And this is the this your interface. So with respect to this plane here, which is dipping towards this, so this part has gone down and this part remain intact. That means relatively it is going up. That means it is a normal fault earthquake, isn't it? Due to normal fault. Okay, so these movements can be detected and measured by this technique. Now, for Nepal, which is relatively recent, in 2015, this earthquake occurred in near Kathmandu, 80 kilometers northwest of Kathmandu. This is the main shock. That is the main earthquake happened, 7.8 magnitude. Okay. And there are many aftershocks, and some of these aftershocks above 6 magnitude. And one of the major aftershock was with 7.3 magnitude. So that occurred here. That is around 70 kilometers northeast from the here Kathmandu is here, 70 kilometers northeast of Kathmandu. And this main shock or main earthquake, it is 80 kilometers northwest of Kathmandu. Now you see, this is how the aftershocks are aligned. Now our interest to see how much deformation, land surface deformation or land surface displacement has happened, whether it is subsiding this your movement or it is the uplifting movement happen. So that is to get that information. Okay, so to measure that, which area has deformed more and what is the nature of deformation, whether it is subsidence or uplift. Now you see, we used this allows this two pulsar data, that is L band data. L band means 23 centimeter wavelength. Now you see, this is for the main shock. So we have used data before and after the main shock or main earthquake. If we process the data and we get this kind of this interprogram, where you see this area that is in and around Kathmandu got uplifted, and this uplift is maximum is 165 centimeter, 1.65 meter. It has gone up due to the earthquake. Then you can imagine this extent of damage it can cause, isn't it? And whereas on the northern part there is subsidence of 60 centimeter that has gone down. Okay, and here is the this is the boundary between these two. This is subsidence and uplift. But this aftershock, which has 7.3 magnitude, again we have processed it before and after this aftershock data, and you see this area has uplifted and this area subsided, but this affected area is much less because the magnitude is much less, and this your movement is also much less because here the uplift is only 65 centimeter. That is also not less. It is quite high, 65 centimeter, and this area has subsided around 35 centimeter. Okay, that also caused a lot of damage. And this is the combined this your picture. Here we have used the data before the main shock and after the major aftershock. Using that data, we get the complete idea about the deformation, land surface deformation of this area due to this Nepal main shock earthquake and all the aftershocks till 7.3 magnitude earthquake occurred on 12th May 2015, whether the main shock occurred on this occurred on your 15th April, and this occurred almost 1 month, 12th May. Okay. Now see, this is the extent of damage happened due to the main shock. You see, this is the this MMI intensity scale. Okay, modified Mercalli intensity scale that shows you how much damage has happened. So this dark red means very severe damage has happened. So these are the areas severe. This very strong. This strong damage has happened, and then moderate and light damage. And if you see this main shock and aftershock all together, what kind of damage has happened? So this the affected area is much more. Here also affected area has been extended. Some more areas have been damaged due to the aftershocks. And we have also observed what happened to the Indian part due to the Nepal earthquake. And you see, this is the situation. So the damage has happened in lobes, not this continuously over the northern boundary, but there are certain areas has damaged more because the certain areas it is more this affected by more this peak ground acceleration because the in situ conditions are not the same. Geological conditions are not the same because of these favorable geological conditions. There are along certain region, their ground acceleration has been enhanced. Okay, so this is the reason why the some of these your lobes there is more damage has happened. Now coming to the this your volcanic hazards, though volcano is not very important for us in our country because we have only this barren island volcano, and that is barren island. From the name itself, you can understand there is no habitation, isn't it? Now, just for knowledge, we should also globally this your competent. So this how volcanic hazard should be addressed. So very briefly, I'll tell you. So before that, how many types of volcano in terms of their this your strength, in terms of the intensity of eruption. So you see from very mild. So this is the Icelandic type. Okay, almost it is a very free flowing this your eruption, and then there is a little bit of this your eruptive power, that is the Hawaiian type. Then the Strombolian, it is increasing this erupting power. Then the Vulcanian is quite high this intensity eruption. Then the Vesuvian and the Pelian, and finally this is the Plinian is the most dangerous this volcano in terms of the strength of eruption. Now see, there are many of the volcanoes has caused this your huge loss of lives and property, and some of the important volcanoes like your Mount St. Helens in 1980. Many, I'm not going to this your tell each in one of them. Like you see Mount Pinatubo, that is in 1991 in Philippines that occurred, and that causes a lot of damage because it happened in the habitated areas in Philippines. Not only due to the volcano itself, but also the mud flow, this lahar, okay, volcanic mud flow or lahar, which is known as. Okay, now our remote sensing can help you to this your study volcano for the mitigations or for monitoring purposes. See, optical remote sensing in many cases it is not very useful. Why? Because during the time of eruption, it is covered by dark this your cloud, this smoke and the dust. But when there is smoke and dust is not covering this surface, when this your smoke can be visible, then you can use this like your shorter wavelength, this your spectral bands, like your blue band or ultraviolet band, even up to the green band, where the smoke can be detected and this your active volcano can be identified, isn't it? Now, thermal remote sensing is very important because in thermal remote sensing, you will get the temperature of the land surface. Here, the temperature of the volcanic vent is the maximum. Okay, and in the pyroclastics, relatively, it is covered by the rocks, so the temperature is not so high. But if you go down where the lava flows happen, okay, so here the temperature is relatively high. So you will get a complete temperature map in and around the volcanic eruption. Okay, and visible this band, how it looks. Okay, sometimes when it is covered by the this volcanic dust or cloud, then you need to use microwave. Okay, microwave remote sensing. So that is nowadays is very important in many of the volcanic studies. And here you see these volcanic lava flows. Here the temperature of the volcanic lava flows, you can differentiate it. And based on that, you can identify which is a old lava flow and which is relatively young lava flow. Okay. Now this is the your Barren Island volcano perspective view, and this is the geological setting. I'm not going to elaborate. Here, this as far as technological advancement, interferometrics are is important and is being used from the mid-90s. You see, this is a very important volcano. Okay, Mount Etna. Okay, this is Italy. Okay, near Italy. So here you see this is the your topographic the view of the Mount Etna. This is the volcanic cone. But here the color, what you see, this gives your color red, green, blue, red, blue, yellow, like this. What is the color cycles you see? These are not topography. These are representing the how much this uplift is happening due to the melt is coming up. So that represents this uplifting movement. So each phase cycle or each color cycle represent 2.8 centimeter uplift along the line of sight of the radar. Okay, so this is how you can do that. So here these movements is only 2 phase cycles. So 2 into 2.8 along the line of sight, there is a uplift of 5.6 centimeter that you can measure, and very precisely also you can measure. Okay, for that there are some more steps you need to follow. So this is the interprogram, and from that we have prepared this kind of this output, and then we have overlay over this volcanic cone. Now you see in case of this Galapagos, this your volcanoes. So there are a series of volcanoes are here, very close to equator. See, there are many volcanoes, volcanic cones are there. Some cones there is no deformation you can see. Almost there is no deformation. So this volcanic cones is relatively stable now. Here at this moment there is no movement is happening, but movement can happen anytime. Like here you see there is a phase cycle you can see. So there is a uplift is happening, but uplift is not very fast. It is relatively slow. But here the number of phase cycles are more, and here even much more. So here 1, here maybe 3, 4, here maybe more than 10. So it says that the rate of uplift you can get from this interferometric study. And if the rate of uplift is more, it is going to erupt in the near future. And where the rate of uplift is relatively less, so there is time. So maybe it will erupt later. So this kind of modeling you can do. There are some model exist using this rate of uplift, and this model you can model then when this eruption is going to happen. Very likelihood time you can identify. And here you see in case of volcano, there is the volcanic mud flow or lahar that causes a lot of damage. As I have told you, that's Mount Pinatubo, that is in Philippines, it happens. So see this 1991, what happened, this volcanic eruption, just before the mud flow, this spread over this area, over this basically the river basin. Okay, you see how this terrain looks like. But this after this lahar has this flowing over this river basin, the entire area was affected, and there are a lot of this loss, huge loss, the number of lives and the property that it caused. Okay. Now there are another very important hazards nowadays in the particularly in the in Indian Himalaya. Like you have reports of many of the cryospheric hazards. Okay, like Rishi Ganga hazard, like your Dharali hazards. This happened. Then there is hazard in the Sikkim, South Lonak. Okay, so there are these hazards. There are some this contribution from the cryospheric this effect and climate impact. Okay, extreme climate, and on the cryosphere, that is the reason. Most of the cases reason for many of the hazards, isn't it? So here this you see cryospheric mountain hazard. So these are essentially exogenous geological hazards in the mountains above the snow line. And then the snow line, what is the snow line you defined is the boundary between snow covered and the snow free surface. But permanent snow line is the boundary beyond which there is permanent snow. Okay. And here you see in case of Western Himalaya, the permanent snow line ranges from around 4,500 to 5,000 meter uh, above mean sea level. Whereas in the Eastern Himalaya, it is relatively at the lower elevation, 3,500 to 4,500 meters. Now the concerns are this, that the cryosphere has been shrinking, and the reason is the climate warming. Due to the climate warming, that the cryosphere has been shrinking. So this is another one of the most important concern in terms of the water resources, in terms of the cryospheric hazards. So this monitoring is very, very important. How the cryosphere is shrinking and what the effect is. Okay, and where is the differential effect and the hazards from glacier and permafrost. So definitely it will increase because of this your climate warming. So prediction, monitoring, and warning of cryospheric hazards are nowadays becomes very, very, very important. And here remote sensing can help along with other these your techniques in an integrated manner, in a multidisciplinary manner. So you can do something uh, uh, towards understanding these cryospheric hazards. I mean, the science of this cryospheric hazard, if you understand well, then you'll be able to do something. You can make some this your genuine attempt for this prediction or early warning of the cryospheric hazards. Okay. So there are these like snow avalanches, glacier surges, glacier debris flow, and glacial lake outburst floods. Okay, so there is a dedicated session on this cryospheric hazard. So I don't need to discuss much on this. Okay, that will be discussed on that particular this session. I am coming to, because we have less time. So coming to this, some of the anthropogenic hazards like mine fire hazards in the Gondwana coalfields. Here you see this is the global the distribution of the coalfields, and in India this is the distribution of coalfields. These are the mostly the Gondwana coalfields. Okay, these are the high quality coal, whereas these are the tertiary coalfields here, here, here. Okay, these are all tertiary coals. These are the relatively geologically uh, they are younger, and these are Permo-Carboniferous, Permian-Carboniferous age, and these are tertiary age. Here the quality is not that high quality, but this is also good enough for this thermal this power generation. Okay, so these are also being used for that purpose. Now you see in case of Gondwana coalfields, and most of the coalfields are affected by coal fire. That is the reason we have been studying this particular anthropogenic hazard from the early 90s, isn't it? And still we have been studying these coalfields. So initially for the coalfield level, individual coalfield level, we have studied like here you see in Gondwana there are 54 coalfields. So each one of them is affected by coal fire. So we have studied some of the worst affected coalfields like Jharia coalfield, for example. And you see from the early 90s to till 2020 or so, what is the coal fire scenario? Sometimes coal fire has been decreased, sometimes coal fire again increased. So this process for coal fire, the phenomenon of coal fire, how it has been migrating from this deeper to the shallower level, how it is migrating laterally, those things are very, very important. How it can be monitored, how it can be arrested. So those kind of this your understanding is very, very important, isn't it? Here you see the red color, it represents the surface coal fire, and the orange is the subsurface coal fire, and the gray is the total coal fire at that particular time. Okay. Here you see Jharia coalfield, surface and subsurface coal fire. This surface is red and subsurface is yellow. And here precisely you can identify where the surface coal fire locations exist using short wave infrared, this your spectral band data. Okay, and here all this coal fire and other mining environmental indicators are placed to have a complete map of this environmental impact assessment due to this mining and this mine fire. Okay. And that is the individual coalfield level. Now this the time for monitoring for the regionally for all the coalfields, and for that purpose we need to use this your large swath image. We used MODIS, which is very, very large swath, some hundreds of kilometers. We have used this SNPP, VIIRS, this image, that is also very large swath. Okay, more than 300 kilometer, sometimes 500 kilometers approximately. And but the pixel size is coarse. In case of MODIS, it is 1 kilometer, and in case of VIIRS, the original resolution is 375 meter. But for finally, what resolution we get, it is close to 1 kilometer only. Okay, but here, what is the beauty of this study, that you can monitor this coal fire situation for all the coal fields together, because you have that much swath, that much image area is available to you. But the problem is the resolution is coarse, so you won't have this very finer scale coal fire this your locations, but you can have the regional this monitoring. So where the large extent affected by coal fire, those areas you can identify. And then this another important hazard in case of this your mining sectors, like your the mine subsidence and roof collapse. That is in case of coal. In case of hard rock mines also it happens, but in case of coal it is more extensive, and the rate of subsidence is also very high, and the damage is also very high. Here we have studied for Ziria coalfield and using different wavelengths like C band and L band. Shorter wavelength is for detecting the slow movements, and longer wavelength for detecting the faster movements. So using slow movement, this detection by C band, and fast movement detection by L band, we have identified the area affected, and then we have combined together, then compared with the ground-based, this ground survey-based, this your observations or the map prepared from ground survey by the mining agencies. We have put it on a GIS platform and combined all this information they have gathered, and then we have compared these two observations. One is from the satellite interferometric surveys, another is the ground-based, ground survey-based, this your observation. So there is a good agreement, and there are some new areas also we have identified. Those areas are not under the purview of the these mining agencies. Rather, they are not at this moment doing any kind of mining in these particular sectors. So that is the reason they are not interested to study such areas. Now you see how this your the rate of the subsidence we have studied by one satellite interferometry base. At the same time, by labeling, we have put number of these ground monuments, and from these monuments we have been monitoring at a regular interval of 3 months or so. And also we have the GPS, these your monuments where the campaign mode GPS survey we did. So using that, we can measure this labeling based subsidence and the GPS based lateral movements. And this is the comparison. You see in labeling, we are getting this, in teams at C band this, and in L band it is little high. Okay. This is how we have worked in a multi-institutional approach, multidisciplinary approach, using multiple institutions like IRS, then your Central Institute of Mining and Fuel Research, that is in Dhanbad, then Survey of India, Geological Research Branch, and also we have worked with Indian Institute of Technology, ISM Dhanbad. Okay. Now coming to the anthropogenic hazard due to groundwater, and we'll be discussing on groundwater depletion, aquifer system compaction, and land subsidence. So you see, this is the this groundwater depletion map prepared by Central Groundwater Board. Okay, so they have using this groundwater level data, they are collecting 4 times in a year. So this is what map they have produced. Okay, that these are the red blocks. These are overexploited blocks in southern India also, and but what's affected area is in the northwest India, that is Punjab, Haryana, Rajasthan, and Delhi. So this is the area, and western part of UP. This is was worst affected in terms of groundwater depletion. Now you see this, there is this mission called GRACE gravity mission. There's twin satellites that measures the gravity or the mass change. Okay, the dynamic gravity or mass change of the area. Based on that, we can have how this groundwater depletion happens. So this shows this northeast part of India. This is there are extensive groundwater depletions happened in around Haryana, Punjab, Delhi, Rajasthan, and western UP. Similarly, there are some degree of ground depletion happens in the southern India also, but here the extent of depletion is much less. This legend is different. Okay, here in this legend it is going up to how much? It's minus 42. here only -5. Okay, you can see this extent of depletion much less, and this is the temporal profile. Okay, so then you see this is the groundwater depleted zones in the regional ground depleted zones in the northwest India, and we have studied the interferometrics are again, and then we have identified how much land surface this your deformation or land subsidence is happening. There are a number of areas we have identified, like mostly in Delhi, in Mohali, Chandigarh, in Gujarat, and some of the areas like your Ludhiana, Hisar, isn't it? So and UP like your Kanpur, Hamirpur. So these are the areas affected by land subsidence. See, this is the picture of Delhi. There are two areas. There are most damage subsidence is happening, and one is the Gurugram and Kapasar area. This is southern part of the Delhi boundary with Haryana, and this is Dwarka area. Initially, there was a lot of subsidence, but now there is subsidence is very low, and some areas there is even uplift is happening. That is in green color I have shown. Okay. Similarly, in Mohali Chandigarh, there are a lot of subsidence happening. This subsidence is more than 10 centimeter in a year in Mohali. In Chandigarh, it is a little less. It is around 3-4 centimeter. There are other areas like Deravasi, this Lalru and Ambala cantonment area, Ambala city. So this area also subsidence is happening. Due to this subsidence, what damage it causes, it is the cracks on the houses. Okay, and this nature of the cracks are of different types. Sometimes it is geometry is vertical, sometimes it is horizontal, and sometimes it oblique. But most importantly, the stress mechanism is different because of the differential movement of the land surface. So sometimes it is tensional, okay, sometimes it is compressional, okay, sometimes it is shear. Okay, so this understanding of the stress dynamics is very important for mitigation, to take appropriate measures for this year, reducing this effect of groundwater depletion. Okay, so with this I finished. I will in time. Okay. So thank you very much. So if you have any questions, you can get back to me. These are my email address. Okay, where you can write to me if you have any questions or any queries. Okay. Thank you. Our next session will start soon. Will be taken by Dr. Somolar Chaturaj. So this is the coordinator, overall coordinator of the workshop. So he will be delivering on this. Okay, the rainfall, recent approaches in rainfall threshold and landslide initiation, numerical modeling, and simulation for landslide early warning system. Okay, I am closing my session. So Dr. Shobhan can start.
To the one day online workshop on uh, the science behind geological hazard for early warning and mitigation. This particular lecture will cater to the obviously in the field of geological hazard, but emphasizing on the landslides, and that too, if we need to understand how the landslide initiates. So in the beginning, what happens there? What are the triggers for landslide? We know that there are some causative factors which basically keep the slope ready so that no, once the trigger appears, the landslide happens. So as for the triggers, so we can understand the triggers can be seismicity, can be rainfall. We have considered here only the rainfall part, and we would like to see what are the recent advanced approaches in rainfall thresholding, and that caters to your landslide initiation, and how based this along with the landslide modeling simulation can help in a landslide early warning system development. So to start with directly, I'll take the audience to understand that there are 16% of the rainfall triggered landslides exist on Earth. So it can be seismically triggered, can be anthropogenically triggered, but 16% of the landslides are basically rainfall triggered. And more than 1.7 lakh people suffer only due to the landslides. This is the MDAT data, our own data. And then in India, around 150 to 200 crores every year, the loss of damage or loss of property will be there. So that's why it is important to understand what causes landslide, what initiates landslide. Is the very basic need of this particular lecture. If we talk about the hotspots of landslide occurrence, so the hotspot basically lies the Indian perspective. We have the whole Western Himalaya consisting of Uttaranchal, Himachal Pradesh, Jammu and Kashmir, and the northeastern states, and recently the Western Ghats as well are contributing in landslide occurrences. So if you see these two photographs, they are basically false color composites showing your landslide. The two different type of landslides are there. And this is the kind of rockfall or landslide which happened in Uttarkasi, and there is a trifurcation. So the landslide material has taken three paths to reach to the ground state. All right. So, what has been the major contribution of landslide in the field of, in the field of landslide from IRS? We have been working in this field for last maybe 30 years or so. So the legacy continues in the field of landslide hazard donation, mapping, and monitoring of landslide hazards. So that basically takes me to understand the landslide hazard and sustainability mapping aided by Earth observation data. The second part, to complement the landslide hazard, we have developed the rainfall threshold models. And the rainfall threshold models globally, it has been seen that it can cater best to development of, at least that can support a landslide early warning system. So here we have developed several equations, threshold equations. We will have a detailed discussion on this. And then last part, but not least, is that once we understand that what are the sustainable zones, mappable zones, once we have done that and we have run our rainfall threshold model, so that basically tells me that when the landslide is going to happen. And then the unanswered part remains still now is your if the landslide happens, how it will happen. So modeling, physical based modeling and simulation basically cater to this very need, where if we have understood the reason of the landslide and to a large extent when the landslide will occur, then the left part is how the landslide will occur. That simply means that if the landslide is there, then what will be the aerial coverage, spatial coverage, which are the villages, roads, etc., that will be coming under the impact zone. So, and then there are several physical parameters like your velocity, like your momentum, height, etc. At any point in the run out zone can we make out so that it can directly help our mitigation. So there are three apex, three vertices that we work with in landslide from Earth observation data. I want the audience to understand first this, that how a landslide look like in a satellite image. So this is from the Nepal, one landslide prone area in Nepal, close to on the bank of Sankosi River. The data is old, 2014 data, but which clearly it is shown here how the landslide look like. So there will be a tonal variation. The variation basically appears the landslide prone area or landslide, while the landslide has already happened, there will be lighter in color, lighter in tone, brighter in tone in satellite imagery. There can be an arc shape, arcuate shape, a curved shape like this. And the third point is that there can be change in a pattern or association in terms of the slope, in terms of the NDVI or the vegetation, and in terms of the drainage. Changing pattern or association means suppose the landslide has happened here, so obviously slope of this portion will not be similar to the slope of that because material has gone down due to gravity. The NDVI value or the vegetation value, obviously this will be freshly exposed rock, so vegetation NDVI value from the rest of the ambient area will be different from this part. And the drainage, so one river, suppose streamlet used to come like this through, earlier it was flowing through this area, another landslide happens and it takes a different least steep path, it drains somewhere else. So that can happen. And conversely, it can happen the river was earlier flowing like this, and now because of the landslide, it takes a path through the which flows through the heart of the landslide now. So both are possible. So there is a change in pattern or association in terms of drainage, in terms of slope, and in terms of NDVI values. So with these 3 points, the shape, the tone, and the pattern association, we can identify landslide as such on satellite images. You can use this technique to identify landslides on simply the images that is available on Google Earth platform, spot images or Landsat images. You can use this technique to visually identify and detect landslide prone area. I want the audience to emphasize upon this fact. Can you see the pondage or the reservoir that has been created? So this is a typical example of landslide dammed lake. And if so, the river flows from this direction, from this way to this way. And if it is blocked here due to the material that has been dislodged by the landslide under the influence of gravity, so it dams basically here, and the lake or pondage is created. You can estimate, if you have DM, you can estimate how much the volume of the water in meter cube is available there. More problematically, if we breach here, if we blast this off so that we can drain the river, the problem will be if we readily blast this off, the whole water that is stored there will come downstream. Earlier it was dry, and now it gasses through this and may create a flood downstream. That quite often, quite some time, it has been happening to this Sankosi river. So whatever this kind of situation happening in the Sankosi in Nepal, Sankosi river in Nepal, that has direct impact in our Indian Bihar, because that river becomes Kosi in India. So that's why any LLOF, landslide lake outburst flood, the water drains downstream and floods the low-lying areas in a substantial portion of the Bihar. So that's why the landslide is not an issue of one country. It's basically international issue. For the first part that we have skipped, we are not going to discuss about how we make the sustainability map, but somehow it looks like this, where we can classify the land piece, our study area, into different zones: very low, low, moderate, high, and very high. They are demarcated by different colors. This is from Ukhimat area close to Kedarnath in Uttarakhand, and we see that these are the landslide prone or sustainable areas. So it is more sustainable. Sustainability means that the causative factors are present there. What do I mean by causative factor? It means that what keeps the slope can be the slope, it can be the aspect, it can be the NDVI values, it can be your distance to stream, distance to major geological structure like faults, lineament density, drainage density, topographic index, wetness index, stream power index, maybe LULC, geomorphology, all these 10, 15 layers that you take together, and then which has to do something with the landslide occurrence, they in amalgamation basically gives me an idea about what are the causations or causative factors for the landslide in this area. So that those factors basically keep the slope ready for the landslide to occur. And someday the rainfall will come, it crosses, supersedes the threshold, and that triggers it, the landslide happens. So we'll focus more on to in this class on the rainfall part, how the triggering happens, how to make the thresholds, etc. So overall, first we make an inventory of landslide where the polygons will be there, and with that inventory, we basically create this the thematic factors like what I have discussed here, like slope aspect, etc. From those, we can make this sustainability map. Once the sensitivity map is prepared, we know which are the red zones, which are the areas which is prone to landslides, and we apply our rainfall threshold there. And finally, we apply the modeling part. Right. So side by side, it may look like this. We have prepared the sensitivity map. We can prepare the vulnerability map as well. Vulnerability is basically taking cues from the elements present, element at stake. That means your houses, your roads, built up area, agricultural land, all these basically they are put at stake due to landslide hazard. So if I can make a map out of that, so that becomes a vulnerability. And sensitivity, I have already discussed, these are the positive factors taken together. If I integrate both these, I get a risk map. So for an area, if the risk has to be high, suppose this area risk has to be high, that means both, as because that is a union, so both your vulnerability and susceptibility have to be equally high, so that the area, so the risk becomes high. If one of them is low, so either of susceptibility or vulnerability is low, then the risk will be low only. So high risk means a bigger thing. High risk means it's not high susceptibility or high vulnerability. High risk means both vulnerability and susceptibility are equally high. So that's a bigger thing. Risk map really matters a lot for mitigation. Now coming directly to how the landslide initiates. So in the last slide, we have discussed about how we prepare the risk map. To understand the risk map, we have to take cues from the sensitivity component and the vulnerability component. But the question often I put to the audience is that if I want to make out the risk of an area, suppose due to a landslide hazard in a particular time, if is my vulnerability and sensitivity is sufficient? So if I have considered these two, will it make all inclusive? So I do not have to consider anything more to calculate the risk. The answer is no. We have to consider the exposure as well. Who are exposed? Which are the people that is exposed? Those are exposed. And fourth is the factor of safety. Factor of safety, what is that? Is basically R by D. R by D. So this your resisting forces by the driving forces. In case of landslide, obviously the resisting forces will be my friction, and the driving forces will be my weight. The gravity, but it's not the exact gravity. Gravity is suppose mg here, and that lies on the slope of alpha, so it will be mg sine alpha, this component, just breaking it along the slope. So this axis, this force that is dragging the material, this material down the slope will be my mg sine alpha. So it is always the tug of war between this mg sine alpha force, that's the gravity, and the friction force that is opposite. The friction can be static friction once the material is stable there, or it can be dynamic friction as well if it starts moving. When it starts moving, there also the friction will be there, that's dynamic friction. So considering both, obviously there will be friction. So there's a war between the competition between the mg sine alpha part and the r part. So this driving force is the mg sine alpha part, and your resisting force is my total friction. Why do I consider total friction? What do I mean by this? Because many times it happens that the phases, this material is constituted of two phases. One is your rock chunks, the hard part, another is water, slurry. So the friction coefficients of rock and the water will be different. So from these two frictional coefficients that is there in the material, we get two different friction values, friction forces. If I add these two frictional forces, we get the total friction. That's why we always consider the total friction versus the driving force, that is mg sine alpha. So that is simply your factor of safety is. So factor of safety can be defined as resisting forces by the driving forces. I want the audience to understand, if my resisting forces are less, that means friction is less, and driving forces are more. If the denominator is more, then factor of safety goes low. So if it is less than 1, that means the resisting forces are quite less. That means if resisting forces are less, then the landslide will happen. Driving forces are more, gravity is more, so the landslide keeps on happening. So that means if the factor of safety goes low, if it goes low below 1, then it means the area is landslide prone, or it can simply mean the landslide has already happened in that area. Conversely, it can happen so that your resisting forces is more compared to the driving forces. So if the resisting forces are more, if the friction is more, that basically helps the material stick to that surface, to the slope. It will not move away. So it will not move downward. So the resisting forces win and the area is stable. So that's why factor of safety more than one simply means that the area is stable. It's not that the landslide will happen here. So we have understood from this discussion that if my factor of safety goes low, especially if it goes below 1.0, then the instability of the slope increases. The instability of the slope increases beyond a point. It may happen that the shear failure happens and the material fails, or material basically slides. In this graph, we need to see how the factor of safety goes down. So uh, this is this axis, y-axis, we plot the factor of safety, that we can measure from an foreign material at a particular saturation at a particular time, instrumentally measurable. So we calculate the factor of safety, and this is my time. So time means, suppose the whole monsoon, I have monsoon months we are plotting. So you start from July 1 and it ends here somewhere in September. So the whole time period is of the monsoon is being plotted here, and the factor of safety is plotting for a particular slope is being plotted here. So for a particular area, factor of safety was supposed at this 5 value or 2 value, 3 value. So it's positive because that is stable. But now what happens? Any slope exposed subaerially, it will undergo the weathering effects. So due to continuous weathering, the of the weathering the and the gullies, etc., working on this, rains coming, freezing and thawing effect, or other simple chemical weathering, the factor of safety has to go low. Slightly, slowly, it goes low, it reaches this point. Then there comes a heavy rainfall because monsoon has started, it is picked up. So heavy rainfall basically lowers my factor of safety. It takes me to this point, lower point. But by nature, uh, natural slopes, they want to stabilize themselves. So they want to get back to their original stability. So the factor of safety again bounces back to this point. It basically, it repairs itself. So it repairs itself, it comes to this point, it becomes almost stable again, and then the weathering continues, etc., and it reaches this point. Now at this point, there happens a peculiar thing, and that is irreversible in nature. What is that? Please see this feature, this erosion at the slope toe. That means at the toe of the slope, there's some erosion. That erosion is anthropogenic erosion. We are using our JCBs, we are extracting material to make a road. So the material mass we are extracting, stripping off, and throwing somewhere else. So that's why there is the erosion. But this erosion is man-made erosion. This man-made erosion basically again will lower my factor of safety because mass is going away. If mass goes away, the the driving force become more compared to the resisting forces. The factor of safety goes down. If it goes down, the point is that it cannot go back again to stability, like what happened in case of rainfall. So it stays here only. This is a permanent damage that has happened to the slope. Why? Because the mass, I have stripped off the mass. The whole mass is gone. The rock is gone, or the material debris is gone. So that's why there's nothing there to support as such. So that's why it is permanently damaged. Again, it continues slowly, then continues. And there happens in the month of, suppose, end July, beginning of August, mid of August, there will be heavy rainfalls, persistent rainfall. So persistent rainfall basically lowers again this factor of safety. It continues like this, it bounces back, tries to gain some stability again, it reaches this point, it continues like this. Again, one fine day, heavy rainfall occurs, it goes up to this point, but still it doesn't touch this line 1.0. So that's why it can again come back to the to some, it can gain to some extent some stability, and it continues there like this. So ultimately there is a slope failure. Since overloading of the upper slope, that means at the top of the slope you are suppose you are building houses, you are increasing your weight, normal weight basically you are increasing. So that basically at the same time, which is saturation is already there, if you do that, then the normal stresses will increase, the shear stresses acting on the body, and shear failure will happen, landslide will happen. And this graph ultimately touches the 1.0 line. So failure happens. That means the landslide happens. So we have understood how in a slope the factor of safety originally was positive and it can be brought down to 1.0 limit. So what has been the feature? What are the features? The features are can be the triggers can be overloading, it can be heavy rainfall, can be persistent rainfall, can be erosion at the slope to it can be the heavy rainfall again, simple weathering. So all these are your triggering mechanisms. So we need to understand from this table that what are the factors. Some are causative factors. I have discussed. They basically keep the slope ready, like the slope, like rock type, structure, etc. They basically keep the slope ready for a landslide to happen. But there comes the triggering mechanism. Then rainfall, seismicity, anthropogenic. We have understood here from this graph that how influential they are to trigger a landslide. If the slope is ready for a landslide, then the trigger comes up and the landslide can happen. We need to understand from here that the role of particularly rainfall in this landslide initiation, landslide trigger. We have been emphasizing repeatedly that landslide, that the rainfall happens to be a trigger. But deeply, very deep, if I think like that, for landslide initiation, the rainfall really acts as a trigger, or it acts as a causation as well. It helps to keep the slope ready. It contributes in the causation. Obviously, it contributes as well in your trigger. No problem in that. It's accepted. Trigger is accepted. But can it contribute in your causation also? Causative factors. Can it condition the slope so that it becomes ready for the trigger to damage? The answer is yes. Rainfall to some extent can act both ways. So it basically keeps the slope ready also, and then can heavy rainfall or heavy torrential rainfalls can with high intensity can be there to act as the trigger. So we need to understand this from this diagram where we have plotted the cumulative rainfall. That is the total rainfall of last 7 days, suppose, or last 15 days, last 30 days in the rainy season. So we're plotting the cumulative rainfall this axis, and again we are plotting time this axis. So what happens? The monsoon starts here. So monsoon starts July and mid-July and July up to this, it reaches this point. So this point will be the critical intensity. This point will be this amount of rainfall will be the critical intensity. Why? Because after this, the slope of the rainfall, slope of the accumulation of rainfall, there is a steep slope. So this steep slope continues for this time till it reaches here where the landslide occurs, the failure happens. So this much of rainfall, this much of total rainfall obviously will be called the critical rainfall. Critical, why it is critical? Because that is leading to reach the rainfall up to this point. So that's why they are the critical rainfall. The amount, the duration through which the critical rainfall happened will be my critical duration. This much duration is critical because that basically is containing the steep slope of the rainfall curve. So critical rainfall and critical duration are required, but where they are acting after the critical intensity has been reached. So this point has to reach this point, the critical intensity, then only the critical rainfall or the critical duration comes into picture. Now, what has happened before the rainfall reaches this point? So what about this part? So this part basically is the causation. So if this is absent, then this point would have been started from this point and it continued like this. So maximum it will reach here. It has not reached the landslide point yet. So landslide will not happen. So it is to be understood that it's not only the critical rainfall or critical duration. This much amount of the cumulative rainfall is also important, and this will be called my antecedent rain. Please mind it, after the antecedent rain only comes into picture my critical rainfall and critical duration. So this part is a trigger, but this part, the antecedent rainfall, is not a trigger. It basically can be considered as your causative factors. So that's how in sensitivity care, they considers your antecedent rainfall as a thematic layer. They think that is also a thematic layer for conditioning the slope that keep the slope ready for landslide to happen. So you may use that way also, or you may keep your rainfall part for your critical duration, trigger only. So that's how the rainfall threshold is to be developed. Now, rainfall threshold, how do I develop? There are different models. So we'll consider one by one. First is that when we are considering only the antecedent rainfall, that means we are considering landslide as a causative factor only. We want to understand whether this rainfall keeps the slope ready for a trigger to appear and cause landslide or no. So what we have done, we have plotted the 15-day antecedent rainfall. So last 15 days, suppose today is 19th, so that means 19th December. So that means from 4th December I start and continue adding the daily rainfalls up to 19th rainfall. 15-day rainfall I have plotted. I have plotted this axis wise, and this axis is my 3-day rainfall. This axis is the last 3 days. So that means if today is 19, that means 16, 17, 18 I have plotted, or 17, 18, 19, I have, including today, I have plotted the total rainfall, I have plotted this axis. Each point, please understand here, each point has a 15-day total antecedent cumulative rainfall value and has one 3-day cumulative value as well. But each point here at the same time represents landslides, or the number of landslides that happens here. Please see the color code. Green triangles indicates there minimum one event that has taken place in that area. 2 events is this violet color, purple color. Blue triangle indicates minimum 3 to 5 events of landslide occurrence has taken place here. And then this color is more than 10 events. So these are these blocks, rectangles. So more than 10 rainfall has happened, 10 landslide has happened in that area. So each of these events, how many events? More than 10 events, but how many in that area? 1, 2, 3, suppose, or 4. So 4 such more than 10 events has happened in that area. And for each of these occurrences, I have got one 15-day and one 3-day value. So that's why they are plotted here. Now the beauty is that if I can draw a line like this, so all my points will be lying in this direction. No point should lie this side. So there is a minimum threshold. That means after this only the rainfall can cause 10 events to happen. Consider this red line. So red line is for 6 to 9 events. All my red points, these brick points, they are this side of the higher side of the threshold. No red point should fall here. That means, what is the beauty of this? Purpose of this? Purpose of this is that this we have made for taking data for from last 10 years, suppose. So the graph is ready. I have prepared the thresholds. Now the 11th year, I want to test it. During the testing season, what I do, suppose on 15th September, I get the data. I get the data of what? Last 15 days and last 3 days. So that will be plotted somewhere here. If it is plotted here this way, then we can tell that, okay, we are on the safe side because it has not crossed even the 1 event threshold. Then suppose it is getting plotted somewhere here. That means we can tell, be careful that 1 to 2 events of rainfall, landslide can happen here. Or suppose the rainfall is that much that season, that year, that it's straight away getting plotted somewhere here. That indicates, the alarm has to be generated. More than 10 landslides can happen anytime in this area because my threshold 10 has crossed. So look at this. T1 stands for the threshold 1, threshold 2 for 2 or more landslides. T3 is the 3 to 5 landslide. T6, T10, there is a more than 10 landslides. And R3 and R15 are basically these values: 15-day total cumulative rainfall and 3-day cumulative rainfall. So in the 11th year, the testing year, I have a plot, I have a point, and that point basically, suppose if it is getting plotted here, anywhere here, so that means that we have to set the alarm. We have to raise the alarm. This one-time event, but we can make it dynamic. We can use it dynamically also. How? The point is that once the graph is there, why not to make a continuous data set for alarm generation? So what happens today is suppose 19 December. So last 15 days from 4th December to 19 December, we have taken the data. And for last 3 days from 17 December, we have taken the data, we have plotted here. This can be done in automation. I ask the software that you automate it and every day you ship the data. So tomorrow, 20th December, last 15 day changes from 5th December to 20th December and from 18th December to 20th December, last 3 days. So it basically continues. We can make it dynamic. The rainfall data anywhere we're getting from the website on the IMD data or something like that. So that every day it updates. So every day that way we can see our new point where it is lying. And in the whole monsoon season, we can see the moment it crosses, my point crosses this line, I can tell T1, it has crossed T1. This line, someday it will cross as the monsoon advances. So it crosses this line and plot somewhere here. That means that my T3 just now it has crossed and more than 3 to 5 landslide as expected in this area. The moment it crosses this line as well, we can tell the alarm is to be generated now for 10 minimum number of 10 landslides in that area. So that's how we can use this. I hope I have made this point clear how the thresholds are made, how the thresholds can be used very simplistic way. Now it happens, especially like events like Dharali, etc., Waynard like event that told us that no, it's not the cumulative rainfall. We have to consider the rainfall as a trigger as well and prepare a threshold. So this chart basically is the intensity versus time. Again, time is this is a log plot. The intensity, time is this way. That means the months this way, monsoonal months, and this is my intensity. Intensity is nothing but the how much millimeter of rainfall in how much time. So per unit time, how much rainfall is happening. So suddenly there is nothing much, and then suddenly last 1 year, like what happens in your cloud burst like situation, last 50 minutes, 10 minutes, there will be heavy rainfall, and landslide is created. So that basically is a particularly landslide is acting as a trigger here. So that's why the intensity matters here. It doesn't matter how back 15 days back, 3 days back, how much it has been happening like. It matters, but here the trigger is more important. That's why we have to consider the intensity here versus the time. And if we plot all the landslide that has happened there in that valley, suppose the points are basically represent the landslides with a particular intensity happen at a particular date. All are timestamp data. This way also we can get a threshold equation. Please understand, this side of this line, this line, there is no point plotted. That means future, when we will be testing that for alarm generation, we can tell if my points is plotting here or here or here, somewhere here, we can tell that we are safe at least. From the data that we have received in the past, from analyzing this data, the same trend, if my points are plotted here, then I am safe. But if it crosses the landslide, I can tell that with this much of intensity in past, with refers to the past, a landslide is expected in your area. That's how the intensity time also helps me to get the threshold. But the point is that the moment we say that it's a 10 years last landslide inventory data, intensity wise or cumulative rainfall wise, there are some aberrations, there are some anomalies that has happened, like what happened in Rishiganga, like what happened in Dharali this year in Uttarakhand, or what happened in Kerala, Waynard. There have been situations like this which basically is an anomaly to the system. It's not in the normal trend. That's why the rate and above. So, but point is that if I make my experiment data, I mean not the testing data, where I'm gathering the data, if I make that sufficiently large enough, so instead of 10 years, if I can gather 25 years data, 30 years data, then this kind of aberrations, anomalies also would have been included in my data experiment, and my test results, my alarm generation will be more better. So there will be less false negatives for alarm generation. So that's the beauty of this kind of. So more input you have, more timestamp data you have in your system for generation of this kind of curve, more better accuracy you at the time of generation of your alarms. I hope I have made this point clear. Okay. Now coming to the next part, that is the rainfall. That is the modeling part. So we have understood that what are the areas which are prone to landslide. The cause from the causes causative factors we can get to know, and from the rainfall threshold, both cumulative and the triggering factor analysis of those, we can get to know that when the landslide may happen. When it crosses the threshold, then only the alarm will be generated. So these two questions are largely remains to be answered. But what remains unanswered till now is if the landslide happens, how it will happen, what will be the spatial cover. That is also very important, equally important to know for us, especially for the mitigation aspects. So that's why we have we are into in this business as well, that is process-based 3D model. So what is here? Basically, all the landslide that is liquefied landslide, we call it debris flow. It's a mixture of rock chunks, soil, and slurry water. A lot of water is there, so that's why they are called debris flow. Debris flow are the main culprits which are to be modeled here. This kind of debris flow happen in Dharali, happen in Wayanad as well. So it's not the big chunks of rock; they happen to be there. Rock falls also happen, but debris flow, as because it's debris, as because a lot of water is there, the spatial coverage increases, and that's why the real damage happens. It from the source area, it can cover kilometers. Suppose 5 kilometers, 7 kilometers it can cover, and then 7 kilometers down there also the damage can happen. So that's why it's important to study debris flow and model debris flow. Why it has to be modeled? We have understood this, that the study has to go beyond the hazard donation and it's objective. That means that what we do here, sitting here, and another somebody doing in another country will get the same model results, as because this is the physics based or math based approach, and it maintains the objectivity. To start with this kind of businesses, this kind of modeling, we need to choose a source of DEM. Some DEM sources are free, and some like your that is in TLS or UV borne DMs. I mean instruments that also give me DMs, but they are in centimeter millimeter level, and obviously the data will be quite large, and we need a very hi-fi system, good system to handle process this data. Otherwise, you can be happy with this allows pulsar 12.5 data. That is beautiful data, but that is old, 2008-9 mostly. But the coverage, spatial coverage, if you see from 60-degree lat to north to 60-degree south, the coverage is there and for the whole globe. So you can get to download this data freely. Anybody can do. And once we have a DEM data, we start our main modeling part. So what we calculate here, we calculate these four physical parameters: the height, velocity, momentum, and pressure. They're the outputs from this modeling model. How it works? We have already discussed this part, where the mg sine theta is basically being opposed by friction, and there's a tug of war between two. So to the model, the governing equation becomes that mg sine theta will be equal to s, equal to or greater than s. The moment the gravitational forces wins, then over the total friction, then the flow will happen. So first input parameter, we have to give a DEM, and on that, from the image, you have to detect what is the source area. The source area basically is a KMZ file or SEP file. If we put that on the DEM for that area, whole area, the height, average height, the software knows, it calculates the volume. Once the volume is calculated, we have to give as input the density of the rocks or the material. So from that, if the density is known, the volume is known, mass is also can be calculated. So this M, that's how the software knows. G is known, theta from the DEM, the slope of the slope is already known. So mg sine theta, the software can calculate. And for the frictional values, for this total friction, we have to give two input to the software. That is the frictional coefficient due to dry friction and the frictional coefficient due to viscous turbulent friction. That is basically due to the liquid phases water, and this is due to the dry phases. So if we add the friction arising out from the dry phases with the friction arising out of the liquid phases, then we get the total friction S. And the software understands that whether mg sine theta is more or your frictional force is more, which force is more. And if this is more, the slide will happen, the model can run. And as an output, as I have told, the velocity, the pressure, momentum, and the height, we can get to know. So the model looks like this, where this is the source area and the model is shown here, the simulated model with the spatial aerial coverage. So at any point, suppose at the road area, you want to know the height of the material that is coming down with, or the velocity, or the momentum, or the pressure. All these are very important to know for remedial measures, because the height, if I know at this point at the road, so that means if I have to arrest this flow, I have to construct a concrete wall to digest the thrust, or so that it can be hampered flow. It doesn't come to the road as such and block the road. So the height of the wall should be more than the height of the material that the flow is coming down with. So that's why the height is important. The velocity is equally important because momentum is important. Knowing the momentum basically helps me how strong, how competent this civil structure, the wall, concrete wall has to be so that it can digest the impact. So that's why they are important to know. So these will be my source areas like this, and the flow. Please see that in the flow area, already two villages are here. This is from Mukimat area, and then the landslide happens in 2012-13. There will be situations like this. I've shown this you before as well. There will be trifurcation. There's a trifurcation happening here, and the slide basically moves this way, and this way. See the model. Model also follows the exact path. From this, you can get to know how accurate your models are, so that you can tell that no, it's in a state where the model results can be communicated to the state authority for mitigation purpose. In Kedarnath, I put one example where this is the city, Kedarnath town used to be the city, and two debris flow or the landslides. Can you see they are very prominently occurring here, and it is sufficient enough to block the river. That's why the river was blocked here, and it took a path like this through the Kedarnath city. Earlier, it was flowing like this side, and now because of the blockade that happened in 2013, so it took a path. It had to go this way, and it flowed through the heart of the Kedarnath. That's why the devastation was that much. So my point is that the landslides, as the geological hazard, is posing a real threat, and they are big landslides, big flows. So they bring sufficient material to block the river. Once the river is blocked, two things can happen. One is that if another channel is available, least resistive path, it takes that up and creates a new river. Or if it is completely blocked, a pondage will be created upstream. And once that is blasted off, the pondage will move downstream and floods the area in the downstream, which were earlier it was dry. We have modeled this. We put the model results from the Kedarnath area to see that the velocity, height, and the momentum, how it varies. So anywhere you click, you can get to know. You will get to know the value of this. Debris flow 1, if you remember, that was happening immediately north of that. That was 1.5 kilometer total run length. That means that big landslide, and the simulated maximum height was 4 to 6 meter, and simulated velocity at the bottom part is 5 to 7 meter per second. It's huge enough to block a river. We have tried this in other areas where we didn't take the DEM input from the space-borne data, satellite data. We tried the UAV-borne, and we have seen if we compare the DEM from the space-borne and DEM from the UAV-borne, the result gets better. So we are more accurately, we can know what is happening where, and we can predict. That helps me for better mitigation, better prediction. Same way we have tried to do this in other areas as well. This is one example from the southern part of India, from the Malin area in Maharashtra. One event happened in 2014. Please see, this is the village before the landslide happened, and how best the landslide has been captured in our own list for data, and has been photographed as well, modeled as well. They are post-factor analysis. That means once the landslide has happened, we are trying to model that. That is the one approach to start with in this modeling business. Why? Because if you do not wet your hands in this, if you do not have sufficient idea how to run a model, then directly onto predictive modeling you just like cannot go. So that's why post-factor analysis, several post-factor analysis, I prefer the operator has to perform first. So we have tried with this and understood that the coverage was this much with the velocity, height, momentum, pressure varying like this. And then we tried our predictive modeling somewhere else with this knowledge with developed. So predictive modeling means the landslide didn't happen till now, has not happened till now. In future, it may happen, but we are keeping our models ready so that when it happens, when the rainfall threshold is crossed, we can we can tell the authority that if the landslide happens, these are the villages will be affected, or at the road this much of material is going to come down, going to be deposited with this much velocity it will come. So that's exactly what we can convey to them. So coming to the last part of this, what we can conclude from this session is that our model height, momentum, velocity that has happened, that we have seen in the debris flow 1 in the Kedarnath area, that was more dangerous and that blocked the river, and consequently it has caused a flood in the temple area. Numerical simulation and flow modeling can be used for calculation of vital physical parameters like your velocity, pressure, momentum, etc. And shear strength parameters can be used for validation. Future potential flows in terms for debris flow, because many times it is a complex landslide, so it's not one time the material goes off. Sequentially in every year, slowly, some more material starts to dislodge and the landslide increases at the source area. So that's why if you have a model, future potential flows also can be modeled and can be told that way. There are several limitations. We have to understood that these models showed that there will be deposition. There will be deposition at the base only, but en route also it will erode, and en route also it will deposit some material. So what till now it has been doing, it basically considers the source, the material from the source, total volume, and it makes it flow down and get deposited there. That may not be exactly the correct case. So what are the take-home points? We have understood that most of the landslide in Uttarakhand have a major debris flow component, and that travels some distance that causes enormous damage and growth. Landslide hazard and susceptibility mapping aided by earth observation-based techniques and analysis of geoengineering aspect has led to damage assessment till now. That basically takes cues to understand your causative factors and help me to develop uh, the hazard map or the susceptibility map as such. And then comes the simulation. If you want to comprehensively assess a landslide hazard, then process-based modeling, what we have understood till now, is to be done. Then analysis of simulation and models, flow events in post-factor and predictive both in this region has helped me to get the important flow physical parameters like pressure, momentum, velocity. We have not included here, but we have to mention the role of the cumulative rainfall and the intensity of the rainfall as the causative factor, as the trigger as well, to understand the initiation of the landslides. We have understood this also, that if we have a modern techniques which basically captures images the land surface like LIDAR, or if we have a drone based DEM instead of satellite based, obviously if they change the platform, then the resolution can be better. But mind it, if the resolution is better, then if the DEM is centimeter level spatial resolution, but it comes with your burden of processing that, and for processing those, you require a good system. To start with, you can choose a small area perhaps, and the future potential debris flow nearby vulnerable locations also. In case of modeling, it can be modeled, because geology, geophology as such cannot change just like that. So once you have modeled here, a post-factor analysis you have done for a landslide that has already happened, you have seen the spatial coverage of landslide exactly follows what is there present in nature. You are sure, so the accuracy goes up, and as well as your confidence also is up. Now with the same experience, same geotechnical parameters like your frictional coefficient mu and xi, etc., those frictional coefficients you apply in the adjacent area if the geology is same, right? Because this is established, this is proved. So with this inputs, you apply somewhere else adjacent area where the landslide is yet to happen. So you do a predictive modeling and please see that how it is flowing. So that way you can do the future potential flows also can be modeled, can be mapped. Some publications that will help you with this is exhaustive list, and it can be later on also. We also can be contacted through the IRS channel, and for further clarification, further questions, or if you are interested in getting some material, some publication from us. So that's where I thank you and stop my presentation. I hope you have understood the basic of how rainfall thresholds and how numerical modeling can help in landslide mitigation. I take 2 minutes break and then I can take up the questions as well. Thank you so much.
Thank you, sir. Next session will start 2:30. Just announce.
Uh, Jonathan, can we ask for the questions? Take up the questions now.
Yes, yes.
It will
Question.
be available in the chat box, right?
Yeah, we are posting, sir.
All right. So I'll take a 2 minutes break to give the answers, right?
Yes.
Okay. Thank you.
Okay.
questions? Few questions are on board, so I try to answer those. Arzu Kumar has asked, what are the main geological hazards in India that you focus for early warning? Main geological hazards in India obviously will be, first will be seismicity, the earthquake, and second will be a landslide, or both have equal weightage. And less importantly, we have some volcanic eruptions as well, but that is should be quite less, at least for the early warning perspective, because nobody lives there in the, the population is quite less in that close to that island. So if we take that out, the volcanic one, then major remains to be with your seismicity and landslide, that where landslide, while early warning or forecasting can be done as per the geological hazards. Thank you. Vipul Bhama has asked, how do real-time sensor networks, soil moisture, pore pressure, I guess pore water pressure, GNSS enhance the predictive capabilities of numerical landslide models within LEWS? So within LEWS, if I break the question, you want to understand the capabilities of numerical models. So numerical models are basically predictive models, if you mean, and predictive simulations. Obviously, the role of soil moisture, pore water pressure, or GNSS, where you can make out that how fast it is moving, tectonics wise, or even non-tectonic movements as well. There's a displacement, suppose, non-tectonic. They are the very good proxies, very good signatures to tell that the landslide can happen there. Soil moisture and pore water pressure, as such, pore water pressure, it's basically the water. It's basically the rainfall. Again, I have discussed here rainfall, how best they can address this issue. Rainfall can act as trigger, can act as your causative factor. We have discussed a lot about this. Soil moisture perhaps is something directly related to the development of sustainability. So that is a causative factor. GNSS are signatures that can tell priorly if displacement is happening. In case of slow moving landslide or creeps, they are particularly important. So they are proxies that will tell that the slope needs some kind of remediation, and if not remedies provided, anthropogenic, human made, then there will be situations like Joshimat, etc. So your question is correct, but they are not directly embedded, or their input is not directly considered for a simulation. Simulation works with a simple phenomena. My force is available for resisting that, and my force is available for driving. So the frictional parameters are the mass, the volume involved, and the angle of repose, angle of internal resistance. They matter more here. Thank you, Vipulji, for your very good question. Vipul has put another question. Do earthquake-triggered landslide often reactivate during the following monsoon season without seismic activity? Do earthquake-triggered landslide, seismically triggered landslide, often reactivate? So seismically triggered landslide, that means once in past they were seismically triggered, I guess, and they now become reactivated during the monsoon season. This is again a very good question. Yeah, obviously, if the slope once has been disturbed, they deserve to be equally reactivated in the monsoon, next monsoon. High probability is there without any seismic activity. The question is very good, and but the point is that it is seismically triggered. So landslide was seismically triggered. So landslide slope was disturbed, and signatures are present there. So once the landslide has happened on satellite image, or if you go to field, you see that in your own eyes, you will see that there are some signatures where active landslide or old or stabilized landslides will be was there. So there will be amphitheater shape. The vegetation has regrown, but the vegetation path will be something else. The type of the vegetation will be something else compared to your surroundings. So these kind of signatures will be there. So the area where the seismically triggered landslides were there, they already zeroed in on, already earmarked. And the people will keep watch on that, because obviously during the rainy season, rain additionally can play a trigger to reactivate that. Thank you. Next question is, why do slopes with identical rainfall exposure show different initiation responses? Identical rainfall exposure show different initial responses depending on the vegetation type, rock strength, soil root interaction. So you yourself have asked the question and you yourself tried to answer this. All right. So if I want to refine this answer, what you already have given is like this. The identical rainfall obviously will be there. ISO rainfall lines will be there, and you are quite correct to mention that the response due to the rainfall will not be same everywhere. You know, apart from what you have already mentioned, the different types of vegetation, soil strength, or rock type, there's another phenomena that often we miss, but that is very, very fundamental, I tell you. It's basically the interaction between the slope amount and slope direction with the bed or the rock type which is there, which is going to be slided, suppose. So the deep of the bed, deep direction and the amount of the bed versus the slope direction and the slope amount. So if my beds are dipping this way, so slope is dipping this way, right? And the beds also dip this same way, then there's a chance that landslide easily can happen. So that's why the same rainfall, one slope suffers with landslide, others do not, because that slope appears to be appears to be rather stable, where the slope is this way, but the beds are dipping opposite side towards the hill. So whatever you do in this kind of conditions, if you construct the road, bring the JCB, wash up the material, but still it remains the same. Everywhere during the road cut, you do not have landslide at some points only. So those points, if you look at it, you will find that your slope and the deep of the beds, they remain to be almost same. Obviously, the amount also matters. So it's the interaction of these two fundamental criteria, along with what we have mentioned, the type of the vegetation, the type of the rock strength, obviously does matter. I hope I have answered your question very clearly. The next question is, why do some slopes fall under low intensity but long duration rainfall, while others require short intense cloudburst rainfall? Very good question again, where you basically want to know the why the trigger. It's basically the fundamental question. Is the rainfall has to be taken in some cases as a positive, in some cases it acts as a triggering mechanism. Some slopes will fail where the intensity of the rainfall is more. It has, within a short period of time, a lot of rainfall has happened, and where basically long lasting rainfall is causing the landslide. So to answer this, largely, basically, you have to consider what material, the rock type, how much weather there, what type of joints are present. The joints of the discontinuities, geological weak planes are present. How many of them? They are providing me a weight failure or a planar failure, depending upon their orientation and their interaction with local fault system, if any. The rock type, the strength of the rock type, how much weathered they are, and their weatherability, how much weathering can happen to them in future. All these basically comes into play, and that is where you get a response where the suddenly triggered heavy rainfall creates a landslide, but in some areas it will not. Another interesting thing I would like to tell you that we generally consider these to be a Newtonian flow. Landslide is a Newtonian flow. But some of these landslides, especially situations like where we have the rock type, we have the in situ rock type in a way that the non-Newtonian behaviors also are expected. Newtonian behavior in case of landslide modeling or process-based landslide modeling has not been well explored. What do I mean by this? Newtonian flow indicates that the viscosity of the material remains all throughout same. Easy to model because the forces acting on that physics-wise is easy to derive, and the calculation becomes easier. Non-Newtonian flows are where the viscosity of the material changes spatially. So at the source we have different viscosity of the material, and then at the bottom of the middle part we have different material. That again takes me to consider what type of rock, what type of joint set. If shear zones are present there, talc type material suddenly is present, that will change in viscosity and it behaves like a non-Newtonian flow. In other, because I work on landslide with other planets as well, like your Mars, etc., on Moon. So where I have seen that many times it may behave like non-Newtonian flows, where the viscosity remains, it varies. So with this kind of flow, uh, certain amount of rainfall that occurs to be there, precipitate there in a cloudburst way, torrential rainfall, will may act as a trigger, but other areas it may not act same way. So it may not trigger a landslide. I hope I have answered your question. Thank you. If we do not have any more question on my chat box, I cannot see any more. So we close this session, and I hope you have enjoyed this particular lecture on landslide early warning using rainfall and modeling. And we promise to meet after the lunch at 2:30 with the cryospheric hazard. Another very good faculty will be available with all our expertise to cater to the cryosphere related geological hazards. So thank you,
Yeah.
and we can sign off now.
Thank you, sir. Thank you, sir, for delivering nice lecture. So next session is 2:30.
Good afternoon, dear participants. Welcome back to the one-day workshop in the third lecture. This lecture is regarding the high altitude glacier hazard studies using remote sensing data and the techniques for cryospheric disaster risk reduction. So we will see about the component of cryosphere, what are the cryospheric component, its element, and the hazards related with the cryosphere in the higher altitude. So, before venturing into the lecture, let us see what are the elements of cryosphere. So, when we say cryosphere, what do we mean? What are the elements? Basically, the elements of cryosphere are the glaciers. It can be continental glacier or it can be mountain glacier. Then we have sea ice, we have iceberg, we have ice shelf, we have permafrost, and the lake, glacier lake, and the river ice. So these all elements together known as the cryosphere. Now, one of the element is the glacier. So, what is a glacier? When we should call a component with snow and ice a glacier. So, by definition, a moving mass of ice is known as glacier. A huge body of ice which has got a movement due to its own weight or own gravity is known as the glacier. So, you can see in this picture here, you can see these fractures. So, these are known as the crevasses. They appear on the surface of the glacier because of their movement, differential movement. So these crevasses are an indication of the movement of the glacier. Here also you can see in the this GIF how the glacier is moving. So it has a movement. Now let us see how glaciers are formed. So for the formation of the glacier, the most important parameter is the temperature and precipitation because both are interrelated. So whenever the temperature will be less than 0 degrees centigrade for a considerable period of time, so we will have precipitation more in the form of snowfall than in the form of rain. So, when we will have more snowfall over the years at the same place, and there will be less melting during the summer, then the snow will start accumulating. Over the years, when the snow, which ultimately becomes ice, will be so thick enough to not able to hold its own weight, it will start moving downward under its own weight, under the force of gravity. So that time we will call it a glacier. So it is a huge body of ice by definition which will move. So where do they form? You can see in this picture the distribution of glacier throughout the globe. This is the world distribution wherever the glaciers are present. So you can see blue color. These are the location where the glaciers are present. Here you can see this is the Antarctica. So glaciers are basically present in the polar region, South Pole, North Pole, and also here you can see in North America, South America, Europe, even in the Africa and Asia. This is basically Himalaya. So you can, as you can see in this map, the glaciers are located at higher latitude and even at lower latitude. These are the near to the equator. This is near the tropics. So how glaciers are forming here? Because of the altitude. So at higher altitude, when the temperature is less, we get precipitation in the form of snow, and that snow remains there, and that is how the glaciers are developed at the mountain regions, even in the tropics and subtropics and near equator. So basically, we have based on their location, we can have two types of glaciers which form at the higher altitude and the glaciers which are formed at the higher latitude. So at the higher latitude glaciers are polar glacier and higher altitude glaciers are in the mountain. They are known as the mountain glacier. And about 75% of the world's supply of fresh water is locked up as a glacier ice. So glaciers are major contributor of the fresh water. So we have seen we have two types of glaciers, mountain glacier and continental glacier. So they have different characteristics because they have formed at the different places. So definitely they will have different properties and different behavior, different characteristics. Let us see the mountain glacier. So mountain glacier, as the name says, they are found basically in the mountain region. For example, in Alps, Himalaya, Andes, Southern Alps. These are the regions, mountains where mountain glaciers are located. These glaciers are smaller than the polar glacier or ice sheets. The lengths are greater than width. They cover only a small region. They transform V-shaped valley into U-shaped valley, which we studied it in our class geography. And the glaciers in mountain, they make the land more rugged. Coming to the continental glacier, which are found in the polar region, they cover a very large part of the land. They are found mostly in the polar region, for example, Greenland and Antarctica. As the mountain glacier make the land more rugged, these glaciers make the land flatter and they are on relatively flat ground. The mountain glacier, they move from higher altitude to the lower altitude. But here, the continental glacier, they flow outward from where the greatest amount of snow and ice has accumulated. Now, in the mountain glacier, uh, the largest glacier are stored in the Hindu Kush Karakoram Himalayan complex. Together they call as HKH. Hindu Kush Karakoram Himalaya. You can see this is the all white colored. You can see these are the glacier. This is Himalaya, this is Karakoram, this part is the Hindu Kush. Here Karakoram, Hindu Kush. So together they are known as the third pole because they are storing, they are home to such a huge body of ice and snow that they qualify to be called as the third pole. So we have two poles, south and north pole. Along with that, we also have a third pole as HKH. And why it is called third pole? Because it has a huge uh, storage of snow and ice. And millions of people are depending on the water supplying from the third pole. And this region is also called as the water tower of Asia because it is supplying a lot of fresh water to almost 10 major rivers uh, from here in the different parts of the countries and the countries of Asia. Coming to the mountain glacier, since we have here Himalaya mountain system, which is a very young mountain system, it is home to more than 10,000 glaciers here. So what are the anatomy, how the glaciers exactly in the mountain areas? Let us see in schematic picture. So this is a schematic picture of a mountain glacier. You can see this is the, suppose this is a mountain starting from here. This is the head wall and it is going from here to here. This is the upper part of the mountain and this is the lower part, lower altitude part. So at the higher altitude, what happens, because as we go higher, temperature decreases, right? So when the temperature is less, we have snowfall here. When precipitation will occur, it will occur in the form of snowfall. And this snowfall will accumulate here. So it will form a glacier here. Since the snow accumulate here, this upper part of glacier is called as the accumulation zone. And when the glacier will flow, when it will move downward, it will come up to here. So lower part of the glacier here. Here there is a seasonality. In winter we will have snow here, but in summer there will be some melting from this part of the glacier because it is at the lower altitude. So this part of the glacier is known as the ablation. Ablation means some part of the glacier is getting lost. Mass of the glacier is getting lost in the form of evaporation, sublimation, or melting. So, in the mountain glacier, there are two zones. Accumulation zone, which is the upper part of the glacier, where the mass is added to the glacier. And lower part of the glacier is the ablation zone, where the mass is getting lost from the glacier. And this accumulation zone and ablation zone is divided by an imaginary line known as the equilibrium line or the snow line. So here you can see if this is accumulation zone, this is ablation zone. So it will be divided by a hypothetical or imaginary line known as the equilibrium line. And the altitude of equilibrium line is known as the equilibrium line altitude. So this is the basic anatomy of a mountain glacier. This is how a glacier looks like on the field. So here I have shown you this part of the glacier head wall here, and the glacier starts from here. This fracture you can see here, these are known as the head wall crevasses, or also it is known as the bergschrund. Bergschrund is the line or the crevasse from where glacier starts. So you can see this accumulation zone full of snow. There is no ice here. It is very bright snow here. This is the lower portion of the glacier. This is known as the Appalachian zone. You can see in the Appalachian zone we have exposed ice also, and there are some boulders on the surface of the glacier and some debris also. This line, there are some seasonal melting on the surface of the glacier because it is at the lower altitude. These are the supraglacial channels. So this is how a glacier looks like in the field. These are some of the features related to the glacier. This is a U-shaped valley. You can see here the shape of the valley is U-shaped. This is total whole glacier. As in the synoptic view, here you can see here the accumulation zone with the very bright snow, and this is the downward region of the glacier. This is the ablation zone. This is accumulation zone, and this is a feature on the glaciated region known as horn. It is a pyramid-shaped peak on near the glacial areas. This is crevasses on the surface of the glacier. These crevasses form due to the difference in the velocity of different parts of the glacier, because glaciers form in a very undulated topography. So not all the surface has the same velocity in the glacier, in a same glacier. Some part have higher velocity, some part will have lower velocity. So because of that difference in the surface velocity, these cracks open on the surface of the glacier. So they indicate that the glacier is very dynamic and it is moving. These are some of the ponds on the surface of the glacier. In the ablation zone, you can see debris on the surface of the glacier. These are the particles brought by glacier on the surface of the glacier. And this is a supraglacier. Supra means on the surface. So on the surface, during summer, we have this kind of pond on glacier. We call it supraglacier ponds. This is the moraine, which are nothing but the particles which are carried by the glaciers and deposited at different places. So if they are deposited in the mid, then we call it medial moraine. If they are deposited on the lateral side, then we call it lateral moraine. If they are deposited in the front, we call it end moraine or the terminal moraine. So these are the moraines which are the depositional feature of glacier. Since glaciers are also a geomorphic agent, just like wind, water, glacier also helps in shaping the landform of the surface. So how it shapes by erosional activity and the depositional activity. because of erosional activity. You can see this has formed, or U-shaped valley has formed, and depositional activity deposits these moraines and this debris, and they form moraines. Let us come to the changing climate and the relation of glacier or the cryosphere hazard and the climate change. This we all know that the climate, as the climate is changing, it is changing in terms of warming. That means the temperature is rising. We all talk about the global warming. Global warming is nothing but the rise in temperature. And it has been found that the rate of rise of temperature over years is increasing. So this graph is basically the anomaly, that means the global mean temperature difference. So you can see how in recent years this anomaly is increasing. That means the rate of rise is also increasing. So this is the global picture. Coming to the our Indian scenario. What is the Indian scenario? Here in India also, the global warming is being felt and observed, and the rise of temperature in the Indian landmass is there. You can see here temperature anomaly, it is positive. This orange is Indian and this gray is the Himalayan part. Now coming to the Himalayan part. So you can see this difference. So the anomaly in Himalaya is more than the anomaly in the Indian landmass. What does that mean? It means that the rise of temperature or warming in Himalaya is even more than the Indian landmass or even the global average. So rate of rise of temperature in Himalaya is more than the other part of the world. Now let us come to the Himalayan part at different altitude. This we have seen the global anomaly. This we have seen the Indian versus the Himalayan anomaly. Now let us come at different altitude. So these are the rate of rise of temperature at various altitude. This is the altitude and this is temperature trend per centigrade per decade. Here you can see as the altitude is increasing, the rate of rise of temperature is also increasing. It means as we are going up, as we are gaining the altitude, the rise of temperature is also increasing. Theoretically, it should not, because at higher altitude, the temperature should be low and also the rate of rise should be low. But contrary to that, the rate of rise of temperature at higher altitude are more. This phenomena is termed as the elevation dependent warming. And elevation dependent warming has been observed over the whole Hindu Kush Karakoram Himalaya. So, what is the implication of this elevation dependent warming? The implication is that at the higher altitude, more melting is being faced by the glaciers. So as we are gaining height, since most of the glaciers are located at higher altitude, you can see here most of the glaciers are located in Himalaya after 4,000. And that also most are located between the 5,000 to 6,000. So as we are gaining height, the elevation dependent warming is increasing. With response to that elevation dependent warming, the glaciers at higher altitude are melting faster. So as they are melting faster, the lakes are forming. At higher altitude, new lakes are forming and the lakes are expanding also very fast. This plot you can see, this is the elevation, number of lakes and percentage of increase in the lake area. So both are more at the higher altitude. Here you can see. So as we are going up, more melting is there, more percentage of glacier area is changing and more lakes are forming. Here you can see this is the change in the lake area, expansion of glacier lake between 1994 and 2020 at 4,685 meter above sea level. This is at 4,755. This is 4,875, and even at the 5,550. You can see from this picture, even at very high altitude, more than 5,000 altitude, how the glaciers are melting. And this melting is being observed in the form of this expansion of glacial lakes. In response to climate change or warming, most of the glaciers are retreating. Retreating means their snout. Snout is what? Basically the end of the glacier, where the glacier ends and the river starts. The discharge from the glacier starts. The lowest elevation of the glacier is known as the snout. So as the glaciers are melting faster, the glaciers are shrinking and going backward. That means their snout is retreating. Here you can see an example from the Gangotri Glacier. This was the snout in 1989, and this was the snout in 2019, the blue color. So you see the black versus blue color snout was here. Now the snout has come here in 2024. It further has come here. So this much part of the glacier has ice has got lost. This much part is now no more with the glacier, and this has come backward. So this is the response of the glacier towards the climate change, that the glaciers are retreating. This is an example from Gangotri Glacier. These are some of the glaciers in Himachal. This is one of the glacier in Himachal Pradesh. You can see the snout of the glacier was marked here in 1886 by GSI. So GSI has marked the snout of this particular glacier here in 1886, 1906, 1957, and 1964. After that, the remote sensing data has come, so it was easier to reconstruct, and it was found that the snout has come up to here in 2016. This is again an example of a glacier in the Himachal. So these are the, till now we have seen the scenario of the glacier. Let us see what is the future. This is a projection which shows that for Hindu Kush Karakoram Himalaya, if the carbon emission is slashed down very rapidly, very aggressively, then also there will be 1.5 degrees Celsius increase of temperature in the global, and against to that there will be 2.1 degree rise of temperature in the mountain, and a third of ice will be lost by the year 2100. This is one of the very a scenario which is very normal or very modest. We can say it is a very modest scenario. Now let us come when the carbon emission is slashed. Then there will be a rise of 2 degree global average temperature, and there will be 2.7 degree rise in the mountain temperature, and half of the ice will be lost by the year 2100. Now the very alarming situation will be this situation when the emission will be not when the carbon emission are not cut down, then the global average temperature will be 4 to 5 degree, and the mountain it will be 5 to 6 degree, very pathetic and very alarmingly. And in response to that, 2/3 of ice will be lost by the year 2100. So this is the future scenario, which shows that even strong action on climate change leaves significant melting of glacier in the Hindu Kush Karakoram range. Let us see how we can study glaciers from space. What is the basic of study of glacier using the remote sensing data? This glacier you can see, it is a satellite picture of a glacier known as Samudra Tapu Glacier in Himachal Pradesh. You can see this is very bright part. These are, and there are branches here, and it is coming up to here, right? So as I have shown you in the schematic picture, accumulation zone, ablation zone, and the snout of the glacier, same you can relate it here in the satellite imagery also. this very bright part, because it is very bright, so it should be snow. So this is the accumulation zone. Why I am saying it should be snow? Because snow has a very high reflectance. This is the reflectance curve of a glacier. Here, the fresh snow, you can see this is reflectance curve, reflectance versus wavelength. In the optical region, we go from blue green to NIR SWIRE region, short wave infrared region. So in the optical region, this snow has a very high reflectance, up to more than 90%, about 100%, you can see here. So whatever comes to the snow reflected back, and it looks very bright in the satellite imagery. This is how it is looking here, the fresh snow. As the snow ages, as it turns into ice, 1 year old snow is known as the fawn. So this is very fresh snow, and this is fawn, that is 1 year old snow. You can see the changes in the reflectance, how the reflectance has dropped from 100% to almost 65% in the optical region, about 70%, you can see here. So fawn is, you can see, this part of the glacier, and it has a lesser reflectance than the snow. So this is snow, this is fawn. As we come to the glacier ice, here it has further lesser reflectance. This curve you can see here, it has further lesser reflectance than the fresh snow and the fawn, and it decreases from optical to SWIRE region. Right? This is the glacier ice, and this is again the debris covered glacier, which is basically the dirty glacier ice because it is covered with the debris. This part, this you can see, this is the dirty glacier ice, which has a very low reflectance, and it looks almost like the surrounding. These are the barren rocks. This red portion in the FCC image are the barren rocks. So the debris covered part of the glacier basically looks like the barren areas in the surrounding. As we have satellite data, and now we know how to identify glacier in the remote sensing data, then if we have high resolution data, we can do the glacier mapping. Mapping of glacier means delineating the glacier in the satellite image and estimating its total area, what is the accumulation area, what is the ablation area, what is the elevation of snout, and other attributes of the glacier. Using the remote sensing data, high resolution optical data, we can very easily do the glacier mapping. This is an example how glacier can be mapped on the satellite image. If we have glacier data, we can do the monitoring. I have shown you this example. If we have temporal data, we can either do this temporal remote sensing data, we can reconstruct the snout of the glacier and monitor it. How this is the reconstruction, and this is the monitoring of the glacier snout. This is an alternative to the visiting to the glacier. One way of the monitoring is going to the field and collecting the information about the snout of the glacier, different parts of the glacier, and the other alternative is by using the remote sensing data. This is an example of snow cover estimation, how the snow cover area can be estimated using remote sensing data. This curve I have shown you, this is the basic of remote sensing for the study of glacier. Here, the reflectance of snow, fresh snow, here you can see versus this debris covered glacier. If you focus to this particular part for fresh snow, this curve you can see it decreases as the wavelength increases. So in the optical region, it has a very high reflectance. But as it goes to NIR and SWIRE region, this part, this is the short wave infrared region of the reflectance part band here. So you can see here a little absorbance is there. here a very high reflectance, and here little bit of absorbance for snow. So if we have different bands, we can use two bands, one in the this region and other at this region, and we can combine them to do the mapping of the snow cover area or to differentiate snow from the non-snow. This is known as the normalized difference snow index or NDSI. So NDSI can be calculated from reflectance in bands at wavelength where snow is very bright. That is band 2 in terms of Landsat, or Moody's band, it can be band 1. And where it is very dark, that is band 5 for Landsat, TM, and Moody's band 6. So here the snow is very bright and here the snow is very dark. So when we combine them, differentiate them, we can get snow area, we can differentiate snow area from the non-snow area. So using the NDSI, we do optical minus SWIRE divided by optical plus SWIRE, and using a threshold of 0.4, we can differentiate snow from non-snow. So when we have differentiated snow cover area from the non-snow cover area, it is very easy for me to do the snow cover monitoring, how the snow cover area is changing during winter or in summer. This is an example of how area of Uttarakhand is changing from January to December. You can see here in January, the white part is the snow area, black is the non-snow area. Here you can see in January, full of almost a large part of Uttarakhand is covered with snow. In February, same in March. In April, some area has non-snow started. The snow cover area has started reducing. We have lesser snow in May, even lesser in June, in July, and less in the August. So August is the period for Uttarakhand when we have less snow cover area, when the snow is minimum. Again, only permanent snow is there during the August. In September, the little snow has started accumulating and again started gaining October, November, December. So this is how using NDSI we can monitor the snow cover areas. Now also we can do the surface temperature monitoring or the estimation of surface temperature, glacier surface temperature. We have thermal data on various satellites. Thermal data means we have information of the temperature in the band of in the bands located between 10.5 and 12.5, where instead of reflectance we get emittance. So whatever we get in the this band region, it is just the emittance from the surface of the earth. So when we have thermal band in the satellite, there are satellites which has got thermal band. For example, Landsat has thermal band, Aster has thermal band, Moody's has thermal band. These all satellites have thermal band. So when we have thermal band in the satellite, we can use the radiance, and when we know the emissivity of a particular feature, we can construct or estimate the surface temperature. This is the formula how we can estimate surface temperature from the radiance. So once we got the surface temperature, of glacier surface temperature, we can also construct how the temperature varies from the snout to the accumulation zone, and also how year-wise temperature is changing. This is how we can estimate the glacier surface velocity. One of the technique is by feature tracking method. Using feature tracking method, we can estimate the surface velocity of the glacier. There are softwares which use remote sensing data, pre-data and post-data, and we correlate them in the software. They find out the east-west and north-south displacement, and then they get the resultant displacement, and using this software we can calculate the glacier surface velocity. This is an example of estimation of glacier surface velocity. This is one of the glacier in Uttarakhand. This arrow shows the direction of the velocity of the glacier, where the features are moving. This is showing the temporal change in the surface velocity of the glacier, how the surface velocity is changing over the years. The velocity of the glacier depends on various factors. For example, the mass balance, how much mass is added to the glacier, how much melting is there, what is the how is the temperature situation. So these all factors affect the glacier surface velocity. Now coming to the hazard part of the cryosphere. Till now we have seen the cryospheric studies or the glacier studies. What is glacier? How we can study glacier using remote sensing data, how we can do the snow cover monitoring using the NDSI, how we can estimate surface temperature using the thermal band data, and how we can estimate the surface velocity. Now let us see the hazards related to the glaciers or the cryosphere. So there are glacier hazards are a major concern worldwide, particularly in the Himalaya, because they have catastrophic societal and geomorphic impacts, and they can cause significant loss of life and livestock. They can cause serious damage to infrastructure such as hydropower, roads, bridges, and settlement, and hence demand urgent attention in light of the ongoing warming. So there are two types of glacier hazard. We can categorize glacier hazards into two categories. One can be indirect and other can be direct glacier hazards. Indirect glacier hazards, they arise as a secondary consequences of glacier feature or process. For example, water resources problem, like the catastrophic water resources problem associated with the wasting glaciers and climate change. These are the indirect glacier hazards. Coming to the direct glacier hazards, they are often referred to as the glacier hazards, which involve the direct action of ice or snow, and they can be ice avalanche, they can be glacier outburst flood or glacier lake outburst flood, or also called GLOW. They are the direct glacier hazards. So glacier hazards are related with the climate, strongly affected by the climate. When there will be change in climate, the glacier will change, and when the glacier will change, that means it is also changing the land use area or the land cover area or the surface of the earth, that part in its vicinity. So change in climate will initiate rapid glacier melting. Rapid glacier melting will cause formation of glacier lake, and formation of glacier lake may give rise to glacier lake outburst flood. Further change in climate can cause slope failure and avalanche, permafrost degradation, slope failure, and the debris failure. Let us see one by one. First, let us see snow avalanche. Snow avalanche is nothing but the mass movement in the glaciated region. It is a type of mass movement. So they are the moving masses of snow that contain rock, soil, or ice, and caused by direct loading of snowfall from large scale weather system of mountains. So when there will be a very large scale loading of snow, and if there will be any change in the slope, there will be chances of snow avalanche. Snow avalanche is nothing but more or less like the landslide at the lower regions. It also has a start zone, it has a track, and it has a runout zone. The start zone, they are basically from where the avalanche originate. It has a crown fracture at the top of the start zone of the slab avalanche. It has a flank fracture on the sides of the start zone, and crown and flank fractures are vertical walls in the snow. It has a shallow stance fracture at the bottom of the start zone. It has a slide path along which the avalanche flows, like the track. It has a runout zone where the avalanche come to rest. And it has a debris deposit, which is the accumulated mass of the avalanche snow once it has come to the rest. So these are the elements of snow avalanche. This is an example of snow avalanche. There are two types of snow avalanche. One can be slab avalanche, which is more or less like your landslide, and one is the point source avalanche. You can see the difference in the two types of snow avalanche. In the point release snow avalanche, it is inverted V shape. It has, in this avalanche, we have powder snow or loose snow. This is the example of the powder or the point release snow avalanche. Then we have slab avalanche. This you can see it is like a slab, when the whole slabs break down and it moves, then it is known as the slab avalanche. Just like snow avalanche, we also have ice avalanche. So ice avalanche also, there are two types of ice avalanche. One is the break type or base failure, other is the ram type or the slab failure. Here you can see from the schematic picture. So break type is basically the hanging glacier typically flow over a moderately inclined bed and end in a frontal cliff where the slope angles increases. Here you can see here when there is an encounter of a very sharp change in the slope steepness, then the this type of avalanche occurs, break type or the wedge failure. Then we have ram type or slope failure, where much larger volume releases from ram type glacier. In these cases, there is no significant change in the slope and the whole ice fails as a slab. So these are the two types of ice avalanche. This is an example of ice avalanche, an event which occurred in Chamoli in 2021 February, and the location is here. This triangle, if you can see here, this is the location of the from where this ice avalanche has occurred here. The same triangle here, and there was a huge body of ice along with rock. It has slided and it has caused a very major disaster in the Uttarakhand, Chamoli district of Uttarakhand in 2021. So this is one of the example of glacier hazards in the mountain regions in Himalaya. So what are the conditions for snow avalanche? How we can characterize them? So basically these are the terrain factors. Snow can accumulate deeply and quickly in mountain areas, increasing the possibility of avalanche. The major terrain factors in avalanche are altitude, vegetation, slope aspect, that means the orientation, steepness, that means the slope, curvature, and presence of snow. So altitude, definitely when there will be increase in altitude, there will be the more chances of snow avalanche. Vegetation, we all know vegetation provides cohesiveness to the surface. So when there will be no vegetation, there will be more chances of avalanches. Aspect, slope aspect, that means the orientation. It has been found that in Himalaya, in the northern hemisphere, the northern slopes are more vulnerable for avalanche than the southern slopes. Why? Because southern slopes, they receives more radiation than the northern slope. So what happens when there will be snowfall? The snow in the southern slope will melt out because of the more radiation in the southern slope. Whereas in the northern slope, the snow will remain there. It will persist because it is getting lesser radiation from the sun. So there will be more accumulation of snow in the northern slope. Since there will be more accumulation of snow, it will be more vulnerable for causing the avalanches. So northern slopes are more vulnerable for the snow avalanche. Steepness, avalanches most frequently occur between the slope of 30 to 45 degree or even 25 to 65 degree. They can occur on any slope under the right condition. Slope profile. The disastrous avalanche are more likely to begin on the convex slope, but they may also begin on the concave slope. And meteorology is also very, very important for causing snow avalanches. If there is rapid weather changes in wind, temperature, snow, rainfall, they can cause changes in the stability of the snowpack. Wind direction, obviously, the wind has power to drift snow. It can just drift from snow from one location and it can deposit at the other location. So the wind can deposit snow 10 times more rapidly than the snow falling directly from the sky. So the wind drifted snow is always found on the steep slope. Wind speed also, it is very important. From high crest snow is known to cause excessive deposition in the depressions and zones of avalanche formation on on level ground where the snow drift glacier may form. So speed over 10 km per hour can transport crystals of diameter 1 to 2 millimeter to a distance of 100 to 500 meter on an average. So wind speed is also one of the very important meteorological parameters for snow avalanches. Air temperature, sudden temperature is also very important because it can change or it can do the metamorphism of the snow. So these are the parameters important for avalanches. How we can study avalanche using remote sensing data? We can find out the susceptible or potential avalanching zone using remote sensing data such as digital elevation model. So using digital elevation model, we can derive various parameters like elevation, slope, aspect, curvature, total water index, and rugged index. And using the optical data, we can find out the snow cover areas. These parameters can be integrated in GIS environment, and using all these parameter integration, we can find out the potential avalanching zones. For example, here. So this is the potential avalanche hazard zonation map of Uttarakhand. You can see red are the very high, blue are high, green are the moderate, and this orange are low, and gray are very low. So this is how we can integrate various remote sensing parameters and we can find the various avalanche zonation. Avalanche is also very prone in the permafrost areas. Permafrost is basically the permanently frozen ground where the temperature is more than temperature is less than 0 degrees Celsius for more than 2 years. So wherever temperature is less than 0 degree for 2 years, we have condition of formation of permafrost zones. And these permafrost zones are important in terms of hazard, high altitude hazards, because as the climate is warming, this permafrost is also thawing. When they are thawing, they are also making the slopes vulnerable for destabilization. So, using the remote sensing data, we can model the permafrost, and when we have permafrost map, we can we can integrate the avalanche susceptible zone with the permafrost zonation map, and we can find where are the high altitude hazards which can occur in the permafrost occur areas or the permafrost dominant areas. Let us come to the glacier lake and the hazard related to the glacier lakes. Glacier lakes are basically the lake which form because of the melting of the glacier. So when the more melting of the glacier is there, the melt water, sometimes they may accumulate in the depressions and they form glacier lakes. There are various types of glacier lakes. This shows an example of evolution and expansion of a glacier lake at the cost of glacier retreat. You can see how the lake is changing its size or expanding between 1989 to 2021. So the size of the area of the glacier lake is expanding and the glacier is retreating. Glacier is retreating because it is melting very fast, and the lake is expanding because again the glacier is melting very fast. This is again one of the example of formation of new lakes at the higher altitude. I have shown you in response to the elevation dependent warming, new lakes are forming at very high altitude, and then also lakes are expanding very fast. This is one of the example. You can see the images between 2008 and 2021. There were no lakes in till 2014. The image of June 2014, image of October 2014. But between after 2014 in 2017, this much of huge lake has formed and it has started growing. This image shows how at the higher altitude, formation of lake has increased and expansion of lake has also increased. So what is happening when the lakes are forming? Also, they are disturbing the ratio between the radiation, absorbed radiation, reflected radiation. Water absorbs a lot of radiation coming from the sun, whereas the snow, they reflect back most of the radiation coming from the sun. So in the scenario when this water is increasing and snow is decreasing, this percentage will change. And when this percentage will change, more warming will be there. So it is a kind of ice albedo positive feedback. Warmer the temperature, lesser the snow, more ice. More ice means more sunlight absorption. More absorption means again more warming. So this work in this loop. So there are various type of glacial lakes. These lakes are Cirque Lake, which is the bedrock by bedrock topography bounded by the hard rock. We call it Cirque Lake. We have lake which form in the front of the glacier. We call it proglacial lake. In this proglacial lake are naturally damped by moraine. We call it proglacial lake. And the glacier on the surface of the glacier is known as the supraglacial lake. So the proglacial lake, we have supraglacial lake, we also have periglacial lake. Periglacial lakes are the lakes which form in the periphery of the glacier. So here again they can be blocked lake also, or it can be normal lake also. And the Cirque Lake, this is the Cirque Lake. So there are various type of glacial lakes. These are again satellite pictures of various type of glacial lake. This is a pro-glacier moraine dam. This is glacier, this is glacial lake, and this ridge you can see this is a moraine damming to the lake. Again, example of glacial lake, pro-glacial lake. This is lake, and this ridge you can see this is a moraine. So it is a moraine dam, pro-glacial lake. These are the supraglacial lake here on the surface of the glacier. This is a glacier body, and ponds you can see. These are the supraglacial lakes. This is an example of supraglacial lake. This is again the supraglacial lake. These are the periglacial lakes. These are glaciers you can see in the satellite image, and these are the lakes. It has formed in the periphery of the glacier. Since they have formed in the periphery of the glacier, we can call them as a periglacial lake. This periglacial lake can be moraine dam or they can be without a moraine dam. This is again one of the type of lake blocked by lateral moraine. So this is a glacier, this is lateral moraine, and this lake is blocked by lateral moraine. Again, an example, this is a lake in the upstream areas of Gangotri town known as Kedartal. You can see this lake, and this is the moraine, lateral moraine, and it is blocked by lateral moraine. So for glacier lake outburst flood study, the prerequisites are doing the glacier inventory. That means finding the glacier name, glacier location, dam type, permafrost condition, and the condition of the lake if it is directly or indirectly related to the mother glacier. So these are the inventory of the glacier lake. This is an example of glacier lake inventory in Uttarakhand. These are the distribution of glacier district wise and type wise. So after identifying or after doing the inventory of the glacier lake, we can identify which lakes are vulnerable and which lakes are not. So first step is to find out the lake which are vulnerable for growth and categorize them into stable and unstable, because not all lakes are vulnerable for glacial lake outburst flood. After identifying, we can find out what could be the triggering of flow. It can be extreme rainfall, it can be rapid mass movement, it can be earthquake, it can be melting of permafrost, or it can be long-term dam degradation. And the glow mechanism can be two types. Suppose this is a schematic picture of a glacier. This is glacier, this is glacial lake. So it can be overtopping mechanism or it can be the piping failure. Overtopping, when there will be more water in the lake, it can overspill and it can cause glacial lake outburst flood. Sometimes even the natural moraine dam can also breach and degrade. That time it will be the piping failure. These are some of the examples of vulnerable glacial lake in Uttarakhand. This is the Safed Lake in Gori Ganga. These are the avalanche zone. Here you can see, and this is the expansion of the glacial lake. This is again a lake in Uttarakhand, Bilangna Lake. You can see this lake, how this lake is expanding in 2016 and 2021. And the location of the lake is also very vulnerable. Lot of loose material, morainic material surrounding to the glacier, which makes it more vulnerable for glacial lake outburst flood and transportation of sediment. Again, Kedartal, I have shown you here. This is the Gangotri town. This is Kedartal. So location-wise also, this is a very vulnerable lake for glacial lake outburst flood. So we can do mitigation for glow by reducing the volume of water retained within the lake, by reinforcing unstable dam, and by increasing the dam freeboard, or the combination of everything. These are some of the examples which has been carried out in the Peru region, how the freeboard of the lake has increased so that the chances of glow are reduced. So there are strategies for glacier hazard monitoring in Himalaya, using the temporal images, doing the assessment of size, doing the permafrost mapping and melting, assessment of natural dam. Using the temporal data, we can do the glacier lake monitoring, and using the SAR data, we can do the stability of the surrounding slope, and using all these parameters, we can do the assessment for the level 1 alert. There are several advantages of remote sensing data for avalanche and glow, because all these events occurred at the higher altitude, which are very located at the inaccessible areas where we cannot go and do the survey. So remote sensing is a very efficient tool and data which we can utilize for using for studying the and monitoring the glacier related hazards such as avalanche and the glow. This is all from my side. Thank you so much. If you have any questions. Sensing help detect landslide earlier than ground survey? I think this question is very much relevant to Dr. Suvanlal Chattoras. He has taken the lecture previous to me, so he will again join. You can ask him. Why does glacier formation require a balance between accumulation and ablation rather than just cold temperature? These are difficult, very different two phenomena. It requires balance between accumulation and ablation to sustain itself. Everything you know, all the features, they should have an optimum equilibrium. They should have to be in optimum equilibrium to sustain. So glacier has to be in balance. It should be accumulation also. It should be ablation also to avoid any inequilibrium condition. And how do internal deformation, basalt sliding collectively determine the flow? It is basically, there are two types of velocity as you have already written, basal sliding and also the plastic deformation. And it depends on where are the glacier. There are two types of glacier, cold based and the warm based, and they have different types of velocity. I will talk more about it when I will talk about the how glacier moves. Why is equilibrium line is most critical control in alpine glacier? Equilibrium line altitude basically is a proxy for mass balance. So when you cannot measure mass balance of glacier, in that condition you can take ELA as a proxy, and it is easier to monitor and easier to measure ELA. That is why it is a very critical parameter in terms of remote sensing to study the glacier health. Why cryosphere is changing? Cryosphere is changing because of it is basically a reflection of climate. Whatever climate is how because for the formation of cryosphere, climate is one of the very major parameter. So when there will be any change in temperature, precipitation, humidity, definitely the cryosphere will change. Why are alpine glacier system extremely sensitive to short term? It is not polar versus mountain glacier. It depends on the size of the glacier, topography of the glacier, how glaciers are responding. It is not that polar glacier are responding slow or the mountain glacier are responding more. But the mountain glacier are, as I have told you, the elevation dependent warming. So they have more warming in the mountain region. So the response time totally depends on the size of the glacier, topography of the glacier, and also in which situation the glacier has formed. So it depends on a many factors instead of cold-based, warm-based, polar or alpine. Why do glacier hazards often increase even when the glacier size is decreasing under climate warming? These both are interrelated. The glacier hazards is increasing because the glacier size is decreasing. When the glacier size is decreasing, it is again giving rise to the different feature uh, which is not familiar to that environment. Suppose in the periglacier area, when the glacier is retreating, it is either giving rise to barren areas, which are again vulnerable for slow failure, or it is giving rise to the glacial lake, which is again vulnerable for glacial lake outburst flood. So change in the glacier size is definitely related with the glacier hazards. I think Dr. R.S. Chatterjee is waiting for the next class. So you can write down my email. If you are more interested, you can always write me and ask me more question. It is pratima@irs.gov.in. Thank you so much.
Yes, Janardhan ji.
Yes, sir.
अच्छा अभी 4 o'clock तक welcome back to this online lecture series workshop on understanding the science behind geological hazard for early warning and mitigation. There has been some rescheduling for due to absence of one of our faculty, and but anyway, nevertheless, all the topics will be catered to by other faculty members. The last one here in this slot was supposed to be dedicated to earthquake hazard, seismicity, and geophysics. So Dr. Chatterjee will cover that part, and that he will take from 4 o'clock to 4:30, and maybe slightly beyond that also. So be prepared to be here in online mode say, till 4:45. Be ready for that. For some time from now, suppose next 20, 25 minutes, 30 minutes, we will discuss about little bit more about the landslide that I feel that is left there. It is basically the first part of the landslide lecture. Generally, I take that way. So where we focus on developing, focus on the mapping aspect, like development of sustainability, vulnerability, risk map, etc. So, as per the definition, as I've told you in the morning, that vulnerability is basically is the capacity of the social, physical, and economic structure to withstand and respond to hazard events. In a way, what I mean here is that it takes care of all the elements present. The elements can be road, the built-up area, the agricultural land. So these are the elements. If I can make a kind of map from that, so that becomes my vulnerability map. Sustainability map, on the other hand, is your uh, is basically the all the causation or causative factors taken together, like slope aspects, geology, geomorphology, distance to lineament, drainage density, SPI, TW, all those which basically keep the slope ready. So that is my sustainability map. And combining these two, we have the risk map. We are familiar with these definitions. Now, the first stage in this, when you are into the landslide, doing some work about research work about the landslide using satellite data. So first thing is that you have to prepare an inventory. Inventory, like many other things, is basically the polygons, active polygons of your presence of landslides. So wherever on surface you can detect a landslide, so you can make a KMZ or shapefile out of that, and these shapefile put in a single GIS layer will be called my inventory. This I am doing basically for the monitoring and the assessment purpose. Then once I come to the vulnerability sensitivity and risk, so we are at still assessment and mitigation only. This we have discussed how the landslide look like. So finally, the hazard generation map will look like something like this. This has been made long before, maybe 30 years back from now, and that is still valid, and a lot many updations is available on this. This shows that this is the Kedarnath temple we have discussed a lot in this morning. This is the temple, and around this we have all my high or very high zones still there. So how do I prepare this kind of map? This particular portion of the lecture is dedicated to that. So how do I make it on using satellite data on a GIS platform? So first, we have to look for the sources. So landside inventory as such, we can take use from, we can generate the KMZ shape files, seeing the data. The data can be simple cartosat data, list for data freely available, or even better, that is available in Google Earth platform. So those images on the Google Earth we can see in 3D, and then we can delineate the area where landslide is actively present. Mind it, that is an active landslide map, GIS map, and that has a time connotation. So 2025 December, I have made the map. Maybe 2024, 26 December, there will be different map, because in between we have the monsoon season, or 24, 23, 10 years back, the map were inventory map was different. They can increase, they can shrink, they can change their dimensions. So that's how the inventory is always time stamped. So you have to, the moment you make an inventory, you have to tell that it is from which data. Next is your vulnerability mapping. Vulnerability mapping, for that we have to take care of the settlement, there is the built up areas, the roads and fields. We'll add this upon and make the vulnerability map. For the sustainability, I have told already, slope aspect, geology, structure, stream, soil depth, vegetation, geology, all these layers. The operator is free to decide more than these layers, or he or she may omit some of the layers depending upon his or her need, depending upon the area. They're all site specific. So maybe some area, if I know that slope is more prominent, more influential in terms of landslide occurrence, so I do not consider other layers, because that is going to dilute my result. And in some cases it may happen so that I am not aware of the area, I have not gone to the field, so these many layers are there. In addition to that, also I add a stream power index, I want topographic wetness index, all these also is to be included. Why? Because I'm not, the operator is not confident that with how many layers I get the actual picture of the sensitivity. So that's why as many layers as possible I consider. So that's how it's site specific, it is operator specific. Right. And basically what GIS exercise, what GIS weightage we give, the algorithm that I follow has been described here. There's a beautiful slide that tells you that these are the layers, so thematic layers. So distance to stream, relative height, slope, aspect, vegetation, all these layers, if I put them together, I get a sensitivity map. But how do I get it stitched together? So that is the algorithm part. So in algorithm wise, what the GIS, ArcGIS or QGIS software is doing, that we need to understand. These are, as I have told, they are all causative factors, conditioning factors. They basically are keeping the slope ready. They are called, each one of them are called a class. So within the class, suppose slope class, we have 5 classes, 0 to 15 degree, 15 to 30 degree, like that. So 5 slope subclasses are there. So each class here contains some of the many of the subclasses, many subclasses. So we have to understand that which subclass has more, which subclass has what type of influence in landslide occurrence. But how do I know that? One way of doing this is that doing experiment. What experiment we are going to do here? We'll cross this slope layer with the inventory layer that we have initially made. Inventory is what? This layer where the landslide polygons are there. So this inventory layer, if I combine with this slope map, if this map and this map is combined together, the sandwich product or the resultant product what it will be shown, it will have the attribute table of this raster image will show that which subclass of the landslide, subclass of the slope layer slope class will have maximum of these landslide polygons, because this has suppose 6 subclasses, and obviously if I stitch these with the inventory layer, then there may be a situation that where suppose 15 to 30 degree content, 30 degree slope class contains coincidentally contains many of the landslide polygons. So that means in a way we can say that these 15 to 30 degree subclass is somehow responsible in landslide occurrence. So that is the inference we draw from here. Similarly, we can stitch this relative height with inventory, stream to distance with the inventory, aspect with inventory, just to understand that each subclasses within this class, how much inferential they have in landslide occurrence. So that basically why we need to know the inference. The inference is basically gives me idea about while applying the algorithm, while applying the GS operation, it gives me idea about how much weight is to be put to which subclass. Because ultimately the subclasses are responsible for landslide occurrence, we have understood. So the subclass that contains in a class, the subclass that contains maximum number of landslide polygons obviously has to be put with maximum weightage, and less other subclasses are not that important. So that is what. So we have to suppose we have this 5, 1, 2, 3, 4, 5, for 9 classes, and each suppose on an average contains 5 subclasses. So 9 into 5 means 45 subclasses are there, which are in a way or the other is responsible for causation of landslides. So 45 subclasses are to be given weights in the algorithm. So we have to derive then 45 weights, and each of these are assigned to the subclasses, one of the each of the subclasses. So that's how we get the weights now. Now, once we cross this inventory with this stream, inventory with the slope, this cross product are stacked here again. So there are 9 classes. So there will be 9 stacked layers. Finally, what we do, we stitch again these 9 layers together to get the sustainability map. So each pixel in this, there are numerous billions of pixels. So pixel here in this subclass tells me what? Tells me information about the distance in distance to stream in meter, relative height in meter, slope in degrees, aspect in degrees, like this. So each pixel. So each pixel here contains information about the weights that is arising out of subclass, all the 45 subclasses. So each pixel supposedly it has information about the 45 weights. Now the operator is free to define a threshold. So how to go with the threshold? The operator decides that 70% threshold rule is something that we go with for this region. What does it mean? It means that whenever highly influential weights are coinciding together for a particular pixel, if the 70% of them are coinciding together, that means they are more influential. So the weights will be initially calculated weights will be either positive or negative. If suppose out of these 45 positive negative mixed subclasses for a particular pixel in your susceptibility, 70% of this 45, suppose 23, 24, 24 positive weights are merging together for that particular pixel, are coincident with that particular pixel. So that's why they pass that 70% threshold rule, and the software understands the most of the influential factors are here concentrated here. So that's why it's very landslide prone area. So the software gives a red color to this. Similarly, we give next step, we give 50% weightage. That means out of 45, 50% of the subclasses, if the 50% of the subclass means 22 subclasses are having positive and they are coinciding on that pixel, they will be given, they are passing your 50% threshold rule. So that means they are moderate. So they will be given a yellow color. Similarly, suppose 10% layer. That means 10% threshold means all out of the 45 subclasses, all my negative values, 19% of the negative values are coinciding together. Only 10% of the positive values are coming together. So that's why it can cross only the 10% threshold. So likewise, that will be given to the safe area because negative values are mostly there, 90% negative values. So that's why the pixel is supposed to be given your green color. So now each of the pixels are color coded. Now the operator asks the software that please classify this. So what the software does, the software depending upon the nearest neighbor calculation, it says that wherever red pixels is wherever red is there, and generally in nature it happens so that if some pixel is supposed to 10 meter here pixel size. So 10 meter pixel within the 10 meter your redness will not vanish just like that. This is the vulnerable area is an area. It's not a pixel. So you have a congregation of red pixels that is given a red color. It appears as a red zone here, green zone here. So it's classified in that way. So this is how the inventory layer looks like, where all my active landslide and all of stabilized landslides are put together, and they are kept in a fashion so that you can see them value-wise. Wherever there is a river bend, they are occurring. Wherever there is a drainage in coinciding, the landslide inventory is occurring there. Landslide presence is there. Just to give a visual estimate. For the vulnerability, I told you that we have to take cues from the element. So here the building is there. So this building, we prepare a map. Or suppose a road is there, the road, building, all this taken together. So, sorry, road is here. So this is my road, that is my road. The roads, we take a separate GIS layer. Agricultural land, we take separate GIS layer. And these layers are added together. This is a settlement, road and agricultural land. Taken together gives me a vulnerability layer, vulnerability map. So in this vulnerability also this classified. The classification says it has 5 classes, very low to very high. So very high means red zone, red color it has given like before. What does it mean? That means, and please see the red zones are coming all along the road. So while adding this, I have given maximum weight to the road layer. Getting so road layer 0.5% weightage and 0.25 I give to these two layers. So if I add this weighted mean, weighted average of these 3 layers, I get a map like this. Right. Similarly, for the sustainability, if you remember, there are different classes. These are my subclasses, and from suppose we get 45 subclasses. So these are my total 45 subclasses, and putting together these, we plot their weights. So all my each of these vertical line represent one subclass. So 45 subclass suppose we have. So 45 vertical lines are there, and this is the 0 line. So that means above 0. So whatever the vertical lines are there, they are having my high influence layer. So high influence 0.74, 0.76, some of the figures have been circled there. So these subclasses are particularly meant for responsible for landslide occurrence. There are several other layers which are not responsible. Please see, they are not responsible. So that means that these layers, these subclasses will not have any role in landslide occurrence. So that is, they're more in number compared to this positive one. So that is why in a layer you get many of the regions are green. Most of the regions are green, only few are red. That is because your subclasses that are responsible, and with this 70% threshold, they are few in number. So that's why red areas will be few. See this, the comparing, if you compare the total green area versus total red area, the red area is only quite less, but they are extremely important to know that where the landslide probability is there. This red zone consists of numerous pixels, and as I have told you, each pixel coincidentally contains, by 70% rule, it contains positive values from those 45 parameters, 45 subclasses. 70% of them contain positive values. So that's why they are given a red color. And the congregation of these red pixels are giving me a red zone. So that's how we know that this area is landslide prone. In 3D, we can show it like this. And then obviously, if you prepare a map, it's not the end. You have to validate this. Any GIS prepared map has to be validated on ground. So how we can validate this? There are different ways. One is RUC, UC curve, AUC curve. That basically deals with the true positives and the true negatives. just to get rid of the alpha and beta statistical error. True positive and true negatives are what? So you go to field, you go to this area, collect samples, you stand, suppose you're standing on a landslide, you take the lat long, correct? So standing on a landslide means that is a true positive, landslide is happening there, they are the true positive. And some area purposefully you have to take where landslide is not there. Suppose on agricultural land, or suppose on a pond, on a lake, no landslide can happen in plain land. So there are your true negative points. Collect suppose 25 such points set from those areas, and some from your landslided area that you can physically verify on the field. So these 50 50 point from your true negative points and 50 true positive points, you have to give it to the software, and software based on that, the true positive and true negative will be compared with this map. With this map, try to get your validation points, true positive and true negative, that you gather from field from all around. Right? It's not that this area only you concentrate and you get all data from, because the software, what it does, it will consider the true positive and true negative, then it compares the true positive and true negative ground truths with this prepared map and give you a value wherever there is a pixel match with the positive to positive, red to true positive, and green to true negatives. There has to be a match. If this match doesn't come properly, if there is a disruption in this precision, then what will happen? Your ROC value will come low. That means they will have low accuracy map. But suppose you have prepared a good GIS map considering all layers, and your true positive and true negative data also is authentic data, that you have ground validated data you have collected, and then you plot it. The software will plot that those points on this map and see where your true positives are matching. How many of your true positive field collected true positives are matching with these red layers, and how many of the true negatives field collected true negatives are matching with your green layers. So suppose 90% match appears in both the cases, then the accuracy, average accuracy will be 90%. But suppose there is a 70% match. That means either the true negatives or the true positive, they are not matching exactly. So that basically tells, because ground data is field validated data, that cannot be wrong. Then there is it references that your map, something to do with your map. Your pixels, red pixels and green pixels have not appeared correctly. So the accuracy has to be increased. How do I increase the accuracy after preparing a map? You have to go back to the basics. You have to check which layers you have taken for sustainability. These 9 layers. Did I miss anything? Or suppose one or two particular layer was most important, others were basically diluting the thing. So omit those layers or give them less weights. Getting? Or suppose I have taken only 5 layers, and I've taken on 5 layer and getting a accuracy assessment done. So maybe the operator has to take should have taken more than 10 layers, 15 layers. All possible aspects has not been considered. So then also your map will not be correct, and you will end up with your low accuracy. Your true positives and true negatives collected from the field will not match with your finally prepared hazard generation map. So that is how we do this. All right, I have, I think. Yeah. Yeah, side by side, if I see, I think I'm close to the this particular session. So vulnerability, sustainability, and then we cross this, we get risk. I told you risk is a big thing. So that simply means that if risk is high, both the sustainability and vulnerability separately and equally, they have to be high. So that's how we get a risk map. We did it for other areas also, like Jamunotri area, which tried to do where from Jamuna River originates, and this is from the Kedarnath area again, but this is quite recent. They are post-disaster. So that's why the sustainability map also has to do with the timing, which time you are preparing the sustainability map. Maybe in later time, the map will not be useful that much. There will be because some addition of some layers, or the layer that you are using for that map, layers have changed itself. LULC have changed. Geology have been modified. There is an earthquake someday comes up, and the lithology also changes. The possibilities are there. So that's why periodically you have to update value at that. I believe I have ended this part. Thank you so much. In 2 minutes from now, I am ready to take questions pertaining particularly to this session, what we have discussed just now for last 30 minutes, suppose. And then once that is over, we'll move to Dr. RS's earthquake one. Thank you so much for attending this. Let us see how many questions are there for this particular session. How thematic layers are integrated to construct a landslide sensitivity map. This is exactly what we have described just now. What algorithm we follow, and the layers, the sub layers, how to put them together, the weights, how do we assign the thresholds, and ultimately how do we get the map. Why risk dynamic changing rapidly with land use, rainfall patterns, slope modifications rather than static like sustainability? I didn't get it. Let me read it again. Why risk dynamic? Why is risk dynamic? Okay, risk is dynamic because the sustainability is time stamped. So if the sustainability has a time connotation and risk considers sustainability, it has also to be time stamped only. So if the sustainability changes, risk also will evolve with time. Why does sustainability changes? At the end I have described if my thematic layers changes, because landform is dynamic, no, geomorphology will change, vegetation will may change. So that's why the sustainability may change with time. Vulnerability also as well will change. Suppose you have this many built up areas now. 20 years from now, there will be a town will be converted to a city. A village will be converted to a town. More roads coming up. So more elements will be there. Vulnerability also will change with time. So that's why the risk has to be dynamic. I hope that I have made it clear. How does human activity, roads, mining, deforestation get systematically integrated with landslide inventories? Human activity, like all anthropogenic ones, if I take together, they are they're supposed to be taken considered under the vulnerability. And as for the inventories as such, if your question is like that, there are new roads are coming up, roads are being built, so that basically creates more landslides. Yeah, that is true. Anthropogenic reason wise, that basically anthropogeny acts as a trigger here to create more landslide. In the morning I've described, I do not know whether you have heard it properly or no. So there is a interrelation between the slope and the the slope of the topography and the bed, deep of the beds, and how the roads, repeatedly we have discussed this, how if you're coming up with new roads, the slope can disturb, and in time, sometime it can fail as well. So thank you so much for your questions. If there is no further question, we close this session, and then suppose very shortly we will be joining with Dr. Chatterjee for his lecture related to seismicity and earthquakes. Thank you so much for attending this.
I may
Yep.
take little more time. Let us start then. Okay, fine.
Uh,
It's not this your long this format, so it will be there will be some gap both sides. Okay.
Okay.
So anyway. Okay. Good afternoon, friends. I am back again, and almost at the end of the workshop today. So today, as we already told you, and this coordinator, Dr. Chaturaj, has already told that one of our faculty stuck up in Delhi due to this cancellation of flights, but that is not an issue. All are here, all are experts. So this last session that is on essentially on earthquake hazards. So that is seismotectonics and active tectonics, then seismic hazards, seismic hazard analysis, and particularly this your co-seismic and interseismic, this your deformation measurements, using particularly the geodetic, this your techniques like your differential interferometric SAR, and sometimes GNSS also, GPS. So we'll cover most of this your part, and some part has already been covered in the previous sessions. Okay. So here we'll also cover bit of geomorphic analysis of active tectonics and neotectonics. Okay. And geophysical investigations. That is very much part of these sessions. Okay, let us start. Yeah. So, this earthquake, all of us know what is an earthquake. So it is caused by sudden movement of a subsurface fault, and the energy which is released, in fact, that was stored as strain in the rock. Okay, that when this stress exceeded the limit and strain exceeded the limit, then this energy is released. So it is converted to seismic waves that in the morning also I have discussed. Okay, that is the elastic rebound theory. This energy is released in the form of seismic waves, okay, which radiates from the earthquake focus. Focus is the origin of the earthquake, okay, source of the earthquake. So this or the beginning of the rupture, okay, in other way. So these seismic waves cause this ground shaking, and this can be measured by seismometer. Okay, but all these waves are not going to make these damages, as I told in the morning. No, this is surface waves are the most destructive. Now this can be measured by the seismometer. That is at it has been shown here. A three-component seismometer records P and AS waves from a local aftershock of the Killary Latur earthquake, the old one. Okay, that I have just picked up how it has been measured. Okay, this is how the seismic waves are measured by the seismometer. Now you see in earthquake, this is very important. All of us or many of us, we know that is the focus and the epicenter of an earthquake. The source of the earthquake or the beginning of the rupture, as I told you, that is the focus, and the epicenter is the point directly above the focus on the surface is the epicenter. And this starting point of an earthquake below ground, where the faulting occurs, is the focus. Now you see these earthquakes, this impact will be the strongest is at the epicenter, in and around that. Okay, sometimes where the rupture is exposed. Okay, so in general it is weaker when it go away, but sometimes the rupture propagates and it exposed at some distant locations. So at far locations, but there will be these damages can be high where the rupture exposed. So that is important. Now you see how this earthquake, this your strength can be measured. Particularly earthquake strength can be measured in two ways. One is what is the energy, that is the magnitude. How much is the energy released, and what is this damage potential, how much damage it does after the earthquake occurs. So this earthquakes measured based on three different scales. So here the first scale is your magnitude of the earthquake. And the other one is the how much the earthquake causes the damage, okay, the effects or the damage of the earthquake. There is another way of doing that. That is the third way of measuring the earthquake is the total energy released by the earthquake. Now you see a seismograph is used to measure the strength of an earthquake, and it produces this your seismogram. That is the this your the output of the seismograph. So that shows the amplitude of the earthquake. Okay. Now in this magnitude scale, this earthquake is scaled into 1 to 10 rating. Okay. So this is the amplitude of the earthquake. So 1 to 10 rating. That is on the Richter scale. That is one of the scale for measuring the magnitude of the earthquake. There is another measuring this style or technique, that is the moment measure. I'm not going to that details. So moment measure is basically how much is the slip the earthquake caused, how much is the surface area of the rupture, okay, all, and this that is multiply, then you will get the total this moment. So this is moment based magnitude of the earthquake. Okay, so but the other way of measuring the earthquake is the intensity of the earthquake, that is the how much damage it causes. So the effect of an earthquake on the earth surface, that is called the intensity, and the intensity scale consists of a series of certain key responses such as people awakening, the movement of furniture, and whether the people feel it or not, whether the windows glasses or window pane they are breaking or not, whether the chimneys are damaged, okay, or this different intensity, and finally the total destruction. Okay, that is the maximum this your value in the scale, that is 12. So it start with 1 when only detected by the seismographs, by the instrument only, but not by the human being. And then 1, 2, 3, 4. In some cases, even if it is very weak, there are some animals can this feel, but this human being cannot feel it. Okay, we can feel only when the magnitude, intensity is substantial. So now when it is 6, for example, okay, then it is felt by all. Okay, but it does not cause much damage, but it can be felt. Okay, when it is 6, but up to 5, it is not all can detect it, and sometimes animals can detect even it is much lower than that. Some animals. Okay, and what I told you that 12, when it is 12 means it causes the total destruction. Now this is the scale. I'm not going to the details that you can get from the any this your the internet search or Google search, for example. You can see this. What is the intensity scale? What it means from 1 to 12. Okay, when 1, 2, 3, 4, 5, like up to 12 means to total damage. Okay, this complete destruction. So now if it is, for example, this 9, 10, that means also there are substantial damage has happened. Now coming to this your tectonics part of this earthquake, that is the science of the earthquake. So now you see this plate tectonics is very, very basic for understanding the earthquake origin. You see there are 7 major these lithospheric plates, and many minor lithospheric plates are there in the earth. And this I'm not going to name each one of them. It is I have mentioned here in the Australian, Eurasian, African, North American, like this. Okay, and there are minor plates are there. Now what is important here in plate tectonics is the plate boundaries. Okay, plate boundaries are basically the zone of maximum earthquake occurrences. In fact, from the geographic locations of the earthquakes, okay, where the maximum earthquakes are happening, from the geographic locations of that, if you draw the lines, so basically you can outline this, what is the plate lithospheric plate boundaries. Okay, so depending on the occurrences of the these earthquakes, one can outline the lithospheric plate boundaries. You see this your statistics of the earthquakes. In general, there are thousands of small earthquakes occur almost every day globally. I mean, there are thousands of earthquakes. Those are of very small magnitude, 1, 2, 3, something like this, up to 3 or 2.5. These are considered as small earthquakes. So they occur every day. That's thousands in number. But medium to large earthquake, where the magnitude is 6 to 8, this is medium to large. that on an average globally once in a month this earthquake occurs. And the strong earthquake where the magnitude is more than 8 or close to that, that occurs on an average 1 in a year. Okay. So, but there is the great earthquakes like even greater than 8, like 8.5, even up to 9, they are very, very rare. Okay. Now you see this nature of earthquakes or the magnitude of earthquakes are controlled to a great extent by the plate boundaries. And there are 3 types of plate boundaries. No, one is convergent, the plate boundary or subduction zones, where the one lithospheric plates going inside the another lithospheric plate. This is known as the subduction zone. So here this which is going inside the other plate, it is destroying. So one plate is going to be destroyed, another one is above it, isn't it? So this is the region of the plate boundaries known as convergent plate boundary. These are the source of the large earthquakes, and they are deeper in general. Whereas these transfer faults, where these 2 lithospheric plates slide past one another with respect to each other. So this is the source of the medium to large earthquakes, and the spreading ridges or the divergent plate boundary where the 2 spreads are uh, spreading apart. Okay, they are going apart from each other. These are known as the spreading ridge, where the crust is created because the melt is coming out. So this is the source of small earthquakes. So here the magnitude is very, very less. Now, here we need to understand this tectonics. There are 3 different this time domains or time scale of the tectonics. One is in general, we call it tectonics, where we analyze the large scale deformation and earth evolution processes at the scale of hundreds of million years. For example, the tectonics in the Precambrian time, the Precambrian tectonics, for example. But neotectonics means the tectonic which is new, neotectonics. Okay, the age wise it is quite young. Okay, so neo represents the age term, isn't it? So few thousands to 10,000, so tens of thousands, not 10,000. So few thousand to tens of thousands and even up to millions of years this neotectonics represents. In fact, the present day lithospheric plate configuration, when it gets settled down, or the jigsaw puzzle, no, these all the lithospheric plates are moving with respect to each other, and the present day configuration of the lithospheric plate, what we see today, the lithospheric plate configuration, when this particular jigsaw puzzle, when it is solved, as you know, analogically, these children plays with this your jigsaw puzzle, and when this everything is matched well, so then this puzzle is complete. Like this, when these lithospheric plates are moving with respect to each other in different directions, when the present lithospheric configuration, when it has achieved, so this is the this your time limit for that particular area. Like in case of India and the Himalayan region, it is around 50 million years. When the this Indo-Australian plate is collided with the this your Eurasian plates. Okay, when just collided. Okay, so then this lithospheric plate boundary has been settled down, isn't it? So from that time onwards, whatever the tectonic activities has happened, that we consider as the new tectonics. But active tectonics means what is presently operating, what is happening today. Today means not just today itself, it's tens to hundreds of years and may go up to the thousands of years. Okay, so this includes this co-seismic and interseismic deformation, what is happening this now. Okay, so for this geomorphic expression exists, and you know the geomorphic expression what remains intact. It is on an average, it is up to 10K, means 10,000 years. One can see what is the landforms, what has been developed 10,000 years back. In general, it is a function of what is the climate of this area, particularly the rainfall and the temperature. So if it is a dry area, the landforms can be retained for even more than 10,000 years. And if it is a very high, strong, the humid tropical climate, a lot of rainfall happens, temperature remains high. So in such cases, it may be even less than 10K. Okay, this is just a general this year observation. Now you see some of this active tectonics, the features. You can see here you can see the highway, how this offset, you can see the road itself, isn't it? Similarly, you can see Similarly, you can see in case of this your deep slip motion here. Okay, just what you see this here the triangular facet and this where is the this offset in the this your ridges you can see, isn't it? So that is basically because of the deep slip fault. Just it's an urgent phone call. Just a few seconds break I'm taking. Okay. That I will discuss. You are going to only apply. So sorry for this interruption. Uh, so I have shown you this. There are two this illustration. One is a stack slip fault of the active tectonic, this stack slip fault, and this is the deep slip fault active tectonics, where you can see the offset of the mountain ridge. Okay, there's the topographic break. And now see this is the in case of San Andreas fault how the river this you're subjected to offset, and in fact it is happening continuously time to time. The river offset from this to this, and again there will be previous course of the river. You can find even this side. Okay, so there is the this when the river offset you find, so definitely it is very recent. Okay, so this can be considered as the active tectonics. Okay. Similarly, here you see that there are some kind of shearing has happened in the northeastern part of the India and in Meghalaya state of India. Here you see the river is showing straight this rectilinear trend, isn't it? And here, just if I show you this, yeah. So you can see this is the soil infilling all along this line, and the river got this trend rectilinear, this very anomalous straight length, and also you can see the vegetation cover in this area, so showing this bend, isn't it? It got bent here. Okay, there is a bending of the vegetation cover from this and this. Okay, that is what interpretation is something like this. There is a fault or this shearing has happened when this is this operating this the movement is this side is towards this and this side is towards this, isn't it? Similarly, you can see this is the thrust fault, and this one block is riding over this another, isn't it? So this is I have taken from the this the internet this figure. You can see this on the hanging wall, that is the riding over the this foot wall block. Okay, this basically a thrust fault. You see this is not only it is moving or riding over this foot wall block, but also there is due to this unique movement there are the fault propagated folding is also happening. This is the fault propagated fold. Similarly, there are many other these landforms. There are characteristics of the active tectonics similar to that what I have shown you, that there is the this your topographic offset, and you will find this alignment of the springs and these triangular facets here. In this case you can see triangular facets are developed, and this your uh, these springs can be there where the this aquifer is cut at number of locations. Okay, so this is you can see, and flat irons also in sometimes when the beds are dipping this opposite to this your fault plane, then you can see this your flat irons. Here you see in this in the very close to Dehradun. In fact, it is the near to Saharanpur area where you see this. There is the active tectonic fault. You can see here, isn't it? In fact, it is no. What I have told you is not close to Saharanpur, but it's very close to Dehradun. It is basically Mohand, okay, in the region. Okay, so here you can see how this your fault plane here, and this is the Sibalix, which is riding over. This is the this IGP, Indo-Gangetic Alluvial Plain. This is the riverborne deposits, and this is the fault plane. And here this is the Sibalic rock. So this is riding over, and this is the fault plane, which is basically the Himalayan frontal thrust. It represents the Himalayan frontal thrust. And in this Doon Valley itself, very close to Dehradun, we have number of active faults where the topographic your break in topographic offset. You can see the topographic break here while along this. Okay, in the Piedmont region. This is in the Piedmont region. So Piedmont region, if you find there is some topographic break, so that means that there is some the tectonics happened very recently, because in the Piedmont region there is the material is loose unconsolidated material, isn't it? So this because of the physical processes of weathering and erosion by the running water essentially. So this gets leveled up very quickly, maybe some tens or hundreds of years, it will be leveled up. But when it remains this topographic breaks still visible, that means it has not happened long back in the past. It has happened only maybe some tens of years or hundreds of years back. It's not much. Okay, it is not very old in thousands of years. Okay, so these are your evidences of active faults, and here this is the example. You can see here the archaeological evidences. This your past houses; those are getting buried, and you can see the bricks of those houses. And this is the locations. Kujnawar is the name of this location. Okay, near Chudmalpur area. You can see the bricks. This one particular age and these bricks of another age. These two bricks, their characteristics are not the same. So there had been houses here, settlements here, and it got buried due to the earthquake or tectonics. Again, people after some years or tens of years or so, people again make their settlements here and with these bricks, and again it got buried due to the earthquake. So repeated earthquakes or tectonics are causing the damages or burial of the houses. And now presently above this, there are the recent houses. Okay, so it should be safe. Okay, there should not be no more tectonic, but essentially this is the region. No, this is the foothills of the Himalaya. That is all very, very tectonically active. Okay, so and this tectonics is originated from the near the about 100 kilometers from south of this HFT, that is near the high altitude zone or this micro seismicity belt in the Himalaya. That is almost 100 kilometers from the Himalayan frontal thrust or from the frontal boundary. Okay, so which is basically the very close to the junction of the main central thrust and the main Himalayan thrust, that is the detachment plane and the main central thrust. So in transition zone is the zone of the major large magnitude earthquakes or great earthquakes. So from these earthquakes, what is happening? This rupture is propagating, and it is finally rupture is getting exposed in the Poland region. Okay, so HFT is considered to be the this rupture of the great earthquake happened in this transition zone. Okay, this is the exposure of the MHT or detachment plane, main Himalayan thrust. Now coming to this geomorphic, this your analysis, multi-temporal geomorphic analysis, particularly drainage analysis if you do. So you can make a drainage map of 1972, 1990, and 2003, what he did. And now presently we have prepared one more drainage map of very recent time. And we see that there are some kind of drainage migration happened. Drainage does not remain static at the same time. So what does that mean? So there is some this your tilting of the drainage basin exist, and this tilting has happened due to this tectonics in this region. And even at this moment, there are some active tectonic movement that maybe the slow creep type of movements are happening. Even today, there are slow creep can be observed from these techniques like interferomatics are. So, so active tectonic movement are reported and we have observed by our analysis. So this from the drainage anomaly, if you observe here, you can see that three different drainage line from 1972, 1990, and 2003 at different colors we have represented. You see that how the drainage line has changed. And see this all along this line, the drainage has shown this sudden change in the direction. From these two, suddenly there is a nick point. It is moving towards this your east, isn't it? The drainage was flowing down towards south and then it is moving towards east. So all along these nick points, there is a major structure is considered to be there, exist. Okay. And you see, there are archaeological evidences can be plotted. For example, at A and B, there are the archaeological remains, very prominent archaeological remains we have observed. Okay, at A and B, and so all along that there may be a major tectonic structure. So there is longitudinal fault exists, that is named as the Piedmont fault. You see, this is what you can see in A and B. Here you see this is very close to Roorkee. Again, here you can see the potteries and the bricks, which is buried at this moment. Okay, and the other one is the this on the Kuznawar that I have already shown to you. Now in crustal deformation model and earthquake, there are initially there are two-stage model exist. There are crustal deformation. One is the strong motion of earth crust and fault rupture. That is the co-seismic deformation. Another is the slow motion and the strain accumulation and elastic behavior of the earth crust in between these earthquakes. That is the interseismic deformation. But nowadays, we are working with this four-stage model of crustal deformation. Okay, and this elastic deformation theory explained that instead of two-stage model, so four-stage model is more convincing. So these two additional stages are like one is before the earthquake happens, that is the pre-seismic phase. Another is the after the earthquake happens, that is the aftershocks, that is the post-seismic phase. Okay, so foreshocks and aftershocks, that is the two more this your stages has been added in the four-stage model of crustal deformation and earthquake. Now here you see there are different kind of spaceborne geodetic techniques exist, and there are some kind of ground-based techniques exist, like electron distance meter, then observation GPS or GNSS, then the satellite laser ranging, then very long baseline interferometry, differential interferomatics are, traditional differential interferomatics are, then advanced differential interferomatics are, that is a time series, this deformation analysis, and the scanner interferometry with the large swath interferometry. Then your DGNSS, similar to the same thing as well, the GPS or GNSS, differential global navigation satellite system and satellite-based gravity anomaly. So these different techniques have different spatial and temporal scale, which is very clearly shown in this particular illustration. Now you see one of the very important technique nowadays is used synthetic aperture radar interferometry or INSAR. See, this is the technique used, okay, for measuring the displacement due to any earthquake, strong motion, or during the interseismic period when the slow movement is happening, even the slow movements can also be detected. But now see what is the principle of this technique? It is the interference of phase of two or more SAR images over the same area, and from these two images, both the images have amplitude and phase. With these, we measure the phase difference of these two images, and from this phase difference, this your path difference is calculated. Okay, and from this path difference, the topography relief, and particularly for this particular session, what is important is the surface displacement can be measured from the wavelength of the radar image. Okay, in this case, that is spatial baseline is also important. So spatial baseline and radar wavelength is important. From this phase difference, we can measure the how much land surface displacements happened. And here you see in case of INSAR, this image output image is known as the interprogram, which is the pixel by pixel phase difference image. And here in this when the phase difference is complete 2 pi radian or one phase cycle. So this one complete phase cycle represents the unit of interferometric measurements, and it is known as a fringe. And it represents 2 pi radian phase difference, and it is equal to lambda by 2. Remember, lambda by 2. So radar wavelength lambda by 2 land surface displacement of the pixels or group of pixels along the radar beam direction or radar line of sight. See, in interferometry or difference in interferometry, in case of interferometry, this terrain does not move, isn't it? So whatever the phase difference we get from the two images, it represents the distance between the two pixels, horizontal distance and the vertical distance. So it is the horizontal phase and the vertical phase. But in case of this your difference in interferometry, that terrain movement is also measured. So in that case, if you take one image today and another image after some days with some time difference, so during that time the terrain has moved. And how it has moved? Because of certain your events like earthquake, like landslide, okay, or slow movement like land subsidence, isn't it? So during that time the terrain has subjected to some kind of movement. So now from this phase difference you can subtract this horizontal phase difference and vertical phase difference, then you will get the your displacement phase or movement phase. And that is the purpose of this your technique in this particular session. So we need to calculate what is the phase difference due to the movement of the terrain, so that from this phase difference we can get how this terrain pixels has displaced due to that particular event of earthquake, or during interseismic period, how much crustal deformation has happened. And what is the nature of this deformation, whether it is a strike slip, represents strike slip displacement, or it is a thrust movement, or it is a normal fault movement. Okay. Now this is how interferometric processing is done. I'm not going to the details of the processing steps. And here precision is a few millimeters. So it is sub-centimeter level precision you can achieve in this displacement of the Earth surface due to earthquake or due to interseismic deformation. Now see, this is the first ever image of difference interferogram that shows the deformation, land surface deformation due to an earthquake. So this is the pioneering study of the difference interferometric SAR. Landers earthquake, this causes the land surface displacement. That was published in Nature, and it was shown for the first time that how due to an earthquake the land surface gets displaced. You can see these cycles, that is the fringes, how it has geometrically oriented. It shows that this movement due to this fault is a strike slip movement. And here you can see this is the white lights. These are represents the this your phase offset, and this basically represents the rupture. Okay. Similarly, here in this case, this is a composite interferogram, and here in one side of this area, this fringes is showing this close fringes, and this fringes shows that the land surface has gone down. Okay, whereas this area, this block remains intact. So that means one block is going down with respect to the another block. So and here is this your fault plane is dipping towards that. So that means it is a normal fault earthquake. So this hanging wall has gone down with respect to the foot wall, isn't it? And again, this is also you can see for the co-seismic slip of the south dipping thrust. So this we have seen, one is strike slip, another is normal fault, and in this case a thrust fault. So this area as going up with respect to the other block. This here the co-seismic slip of the south dipping thrust. So thrust is dipping towards south. Okay, and but they did not reach the surface. But this part is going up. So this is basically the hanging wall is going up. So this is a thrust fault. So just I have tried to show these three different kinds of movement from the pioneering studies on the difference interferometric SAR. Like you see in case of Bam earthquake, Iran, that magnitude was not very high, 6.15, but depth was very, very less, shallow. So if the depth is very less, the damage is much. As well as it depends on also these what are the material in the terrain, what kind of material is there. If the material is very hard and compact, then the effect is less. If the material is loose and consolidated, then the damage is much. And in fact, there is 43,000 deaths and 85% buildings were damaged. Okay, here the insert processing can be done. And this is the first interprogram, raw interprogram. Then it is the difference interprogram, and this is the displacement this your vectors due to this earthquake. For Nepal earthquake, so that is what I have perhaps discussed in the morning. So 7.8 magnitude earthquake occurred 80 kilometer northwest of Kathmandu city. Okay, so here is the this main shock and is the aftershock. 7.3 magnitude aftershock, and see all the aftershocks are aligned in this particular direction. Okay, and there is very less number of aftershock or no aftershock in the western side, but only in the eastern side. So it says something very, very unique. Okay, and all the damages happened only towards the eastern side. Okay, so this is how the rupture has propagated, and finally the rupture is not exposed to the surface. That is also very interesting. So you see, this is the interprogram. Okay, this is from L band and this is from C band. C band shows much more detailed these displacement fringes. Okay, so but what is important here, mostly it highlights this your uplift part. This area has been uplifted, and the uplift is about 1.65 meter, approximately 1.7 meter uplift, and here the subsidence are about 60 centimeter on the northern part. But here this uplifting part is very, very detailed pattern of the uplift you can see, and subsidence part is not so prominent here. That is C band radar set 2. Now you see this is allows 2 for the this main shock, and it is for the aftershock 7.3 and 7.8. So the affected area is much more, and the number of fringes are also much more. Here the total displacement is 65 centimeter uplift in the southern part, and here the subsidence is 35 centimeter. Okay. Now see how we can interpret where this the possible rupture zone, because rupture is not exposed to the surface. So we need to understand how the rupture is hidden underneath, remain blind. So where could be the rupture? Because that is very, very important to derive this. What is the peak ground acceleration? How it can be estimated this from this the location of your epicenter, how the PGA values, peak ground acceleration the values are varying with respect to in situ conditions and with respect to the geometry of the earthquake and the location of the rupture. So for that purpose, the rupture line is important. So we have interpreted the rupture line either this or this. Okay, this is the maximum displacement axis, but this is the this your interface between the two types of displacement, as well as this is the center of the aftershocks or the concentration of the aftershocks. So this is the likelihood location of the rupture line, which is hidden underneath. Yeah, this is what we have interpreted. Now, see this based on this MMI intensity, that is the modified Mercalli intensity values. So you can see this is the main shock, this damage, and this is the main shock and the aftershock damage, and this is how it has affected the Indian part that we discussed in the morning, isn't it? Now we can integrate all the in situ conditions and PGA values and in situ conditions, liquefaction potential all together. Then we can integrate all these together, and we can find out what is the potential this damage area. So this is the potential damage. Okay, this what are the areas, what is the risk of damage, and this is the what is the observed damage. And you can see both are very much agreeable to each other. So that is why this kind of seismic hazard analysis is very, very important. That seismic hazard analysis you can do before that, and based on that you can do this seismic micro zonation. So at the large scale, if this you can prepare this kind of maps, then you can tell that this is the area where the maximum damage can take place because of the in situ conditions. Okay, in situ geological condition, this is the sediment thickness, this your discontinuity planes. There are a number of parameter topography. Okay, all those things are very, very important to understand where the peak ground acceleration, how much it will be enhanced, and what is the extent of damage it can happen. Along with that, what is the area, how it is more prone to liquefaction hazard, or liquefaction hazard risk is very, very less. Depending on that, you can integrate and you can prepare the potential damage or seismic microzonation map. And this is the actual intensity of damage happened due to the Nepal earthquake. Now, this when studying the geodynamics of the Northwest Himalaya, we need to study the small geodetic observations, both interferometric SAR and the GNSS. And nowadays, you know that this your core stations or permanent GPS stations network has been established by Survey of India, although we had by different organizations like Indian Space Research Organization, then NGRI, National Geophysical Research Institute, then Wadi Institute, Himalayan Geology, then MOES. There are many organizations. They have their own these core stations, but these numbers was very limited number. Now, Survey of India has been given this mandate to have this network of core stations, and at this moment they have 1,200 plus core stations all over the country. And all along the Himalaya, there is a comparatively dense network of core stations has been established, and those core station data is available to anybody from the government of organizations, and also from this your PSU and this your private organizations can also access with some conditions are there. So you can access this data and you can get this how much is the this strain is getting accumulated, which the area of maximum strain accumulation, that kind of spatial analysis you can do. And along with that, this interferometric SAR is a very proven technique for analyzing the this geodetic this deformation. So in this case, Himalayan in north-south transit, we have studied these different profiles, and we have seen how much is the uplift has happened, and also what is the horizontal this your this slow deformation is happening. So both we have studied. Here you can see the profiles all along the north-south stretches we have studied, and we have identified some of the important locations where the maximum uplift is happening. Okay, like in and around the MCT, for example. And this is the ITSZ. There are also some subtle uplift we have observed. Okay. Then we can also see in regionally how this strain accumulation is happening for this large swath, this cancer interferometry that we are studying. There are many other organizations have initiated this kind of study. Okay, so and people are trying to find out the areas of this your deformation. So this is the how this interseismic deformation is happening, where the strain accumulation in terms of uplift, in terms of this your this how much slip is happening. So this kind of detailed analysis is being done using this interferometric SAR, and which is integrated with this your course data. Okay. So again, this with this your GNSS observations are very much being done by many of the groups, including this ISRO, ISRO, and this IRS. So we have analyzed a number of locations. What is the course data and this compare mode GPS data, and here we have integrated with that this lineament-based principal stress directions. So from these lineaments, we can identify or we can determine the principal stress direction, and we see that all along this area. So at from south to north at different locations near the foreland. So the boundary at and around in and around the HFT, and towards the north like MCT or so. So we have this derived this what is the this principal stress direction from the lineament orientations. So first we have identified the lineament orientation, then we have identified the what is the on an average what is the discontinuity plane orientation, and then finally depending on the this your this sigma 1, sigma 2, sigma 3, we interpret with respect to the geometry of the this your fault, and then this is the principal stress direction we have derived. This is the principal stress direction, vector main orientation of the lineament, and the principal stress direction or plate motion we have identified. That we have compared with the this what is the plate motion we observed from the GPS observations. So these two things are compared. So this is what our study, and then this morphotectonic analysis, what we have already told you. So you can see this kind of this your subsurface features. Okay, so that we have already discussed with you. And here the geophysics or geophysical investigation like ground penetrating radar is very important and proven technique to get the subsurface profile, the interface in terms of the dielectric interface or the where the active faults exist underneath, that can be interpreted. Like here you can see this is the HFT, underlying there are the IGP, that is the riverborne these deposits, and above it there are the siblings. Okay, and this interface here this your the you can see the scarp surface where if this from the section you can see it very well. But even if you don't see it from the ground penetrating radar, you can see the geometry of the fault. So this is how geophysical investigations have been working. So in a number of locations we have studied that in the foothills, particularly all along this Piedmont region and Piedmont alluvial region. So number of locations all through the Northwest Himalaya we have studied with the GPR, starting from the northern part. This is, for example, this Haryana, even up to Punjab or close to Jammu, but mostly in the this Haryana and this your Himachal Pradesh and Uttarakhand, up to this your Haldwani fan area, all along this belt from east to west, all along the HFT and south in the Piedmont region and Piedmont alluvial region, we have geophysical investigations. Okay, and from that we can see that how in the Poland region the deformation, nature of deformation, and the geometry of the not only the Himalaya frontal thrust, but also there are the active faults which is occurring in the Piedmont region, like Piedmont fault, and number of strike slip transverse faults. With this, I conclude and this session. I think with this, our this workshop is concluded. So you have many questions, I understand. So whatever the questions, you can come back to us. All the emails we have given to you, so you can write to the respective your presenter. All there are we have given this faculty, myself, Arish Chatterjee, Dr. Somunlal Chattaraj, then Dr. Pratima Pandey, and Dr. Suresh Kanoja. So you can see our website and you can see the faculty of the Geosciences Department of Indian Institute for Remote Sensing, and their email address is very much given there. So depending on this, your background, you can come back with your questions and queries. If you have any question or query, you can write back to us. Or if you have any suggestions for any feedback, so you can write back to us. You can write directly to Dr. Somunlal Chattaraj, who is the coordinator of the workshop, or to me. Okay, so or any of the faculty, you can ask the questions or queries, and feedback you write to Dr. Chattaraj or to me. Okay, with this, I conclude. Thank you. Ashokji, it's fine. Is anybody online?
Yes, sir. Yes, sir. So I have pasted some questions on the chat.
There are some questions.
Yeah, yes, sir.
Okay. So then I think all the this year should be there. Depending on the where I am not cannot see this my screen. Screen गायब हो गया. ये है. हाँ, yeah. So in this, so where Ramesh Kumar is writing, Shivalik Hills are the name of the Himalayan systems. Yeah, yeah. It is the outer Himalaya. It is known as the outer Himalaya. Yes, you are right. It is the southernmost. You are very right. Why does the insert fail during large earthquakes that produce meter level displacement? Meter level displacement fails. No. The condition is it is not failing. If the between the pixels, if the displacement, if the between the pixels, if the displacement is more than lambda by 2 between two adjacent pixels, then it cannot detect. But if there is displacement over an area It can be meter, even more than a meter. There is not issue. It does not fail then. Okay. During large earthquake, we can measure that. Only problem is if it is so rapid that between the two adjacent pixels it is more than lambda by 2, then that this phase jump it cannot hit it. So there it fails. That is why in the rupture line where the displacement is more than lambda by 2, so it is there is a decorrelation. That is what happens. Okay. So I am here fails. Why do atmospheric delays sometimes mimic tectonic deformation? Yes, that is a very good question. Atmospheric, this your phase, but it is not very high. See, it is in case of slow deformation, it makes the problem because atmospheric phase may be one phase cycle, and when it is very, it goes even up to two phase cycles, but in general, it is one or less than one phase cycle, depending on your wavelength. Okay. So now, see, if it is C band, it is like this. It is one phase cycle, and when the atmosphere is very turbulent, it can go up to two or so. So when the deformation is very slow, then you need to take care of the atmospheric phase. That you can do by nowadays advanced differential interform discharge. The time series D insert you do, and this atmospheric phase you can separate out. So it's not a problem. And even for the earthquake related things, but earthquake case, it is not very important because earthquake displacement is very high. Atmospheric phase is very small, isn't it? So there is no problem in detecting. Only there is a small problem in the values, very small problem. But if you can correct it also, you can, there are some standard model, atmospheric model that you can make use of that. Okay. So then you can correct it and you can do it yourself using the water vapor. What is there at these two image, okay, from this other satellite data, or you can use some this your model, you can do this correction. What does the next question? What does deep magnitude affect the vertical versus horizontal components of display? See, there is any kind of movements can happen, no, depending on this nature of the fault. If it is strike slip, they are horizontal. If it is normal fault, then it is the all along the fault plane. Thrust also, it is all along the fault plane. Okay, it can be both as well. So, but you can resolve it. You can take two image pair, one is ascending and descending, and from that you can resolve that what is the exactly horizontal and vertical component. And there is standard algorithm now. Just refer to some standard literature, and you can do this. There is equation, and what is the slope, what is the this loop direction or loop angle, the azimuth of the loop direction and the loop angle, and the slope of the topographic this slope. You use it and you can do that. Okay. How does deep slip displacement influence the thickness of the sedimentary layers across a fault? This is not very clear to me. The thickness of sedimentary layers, but deep slip, if it is a deep slip, then there is a vertical displacement. So then you have to take care of the vertical displacement. How much is the vertical displacement that you can do? Okay, and then, and the next question, what Ganesh has said. What Ganesh has said. So, what Ganesh has said that which freely available satellite datasets are most suitable for beginners to study. See, at this moment, whatever data is available, that is Sentinel-1. You have other data that is archived, previously archived data like your ERS or NBSAT, but and some ALOS-1 data also really available, but those data is very, very less. The Radarset-1 also you may get some data, but Sentinel-1, that is the very good data sets are available. The stack of data sets are available. So C-band Sentinel-1 and NISR data start coming. Okay, so NISR, we have both two bands data. This is NASA ISRO synthetic aperture radar data. This is the satellite launched in 30th of July. And now this data has been ready, and some of the data is already available. So this NISR data will be regularly available now. That data you can use, where the S-band and L-band, both the data are available. Okay. In case of L-band, this is good one way because here the decorrelation is less. But the problem is L-band is longer, so it has a lot of advantage. But if the deformation is very slow, and for the event-based deformation, it may not be useful. okay, where the deformation is very slow, okay, then for such cases, you need to use shorter wavelength. So we have S band also, you can try with S band, and also Sentinel-1 data is already available. So that data also you have, you can do that. So here, Aryabhat has asked, how did you identify the areas? What problems you faced? How did you rectify the errors? Areas mean affected areas, what are the affected areas where this is some deformation has happened? You mean to say that? If it is so, then there will be clear-cut signatures, in interferometrics are if that correlation coefficient or the coherence value is significant. So it is not very low, like 0.1, 0.2. If the value is higher, like even above 0.3, 0.4, 0.5, like this, then you can get this prominent differential interferometric fringe. Okay, so this you can find the interferometric signatures. From that, you can identify the affected area where the deformation is happening. Okay, so now what would be the reason for that? It depends on the site, your condition and the geology. So it can be due to, for example, due to the slope. If there is a steep slope area you are working, what is the material type, rock type, whether it is fragile or it is very hard and compact, or if it is their hydrogeological problem, whether it is due to the groundwater abstraction or this groundwater recharge. So in both ways it can happen. So it depends, depending on your site conditions and site nature. And if it is in the higher altitude area, this is for example, it is the permafrost area, for example, then it can be due to permafrost degradation, due to the climate change. So that you have to interpret. Okay, I think with this, okay, there is more questions. How can okay, there is how can this is also question is not complete, but it is a very good question. So groundwater problems, it is problem of groundwater depletion, groundwater storage change, and aquifer deformation, aquifer compaction. If there are more groundwater recharge happen, there can be aquifer dilation also is possible, but that is very rarely happens. This most important problem is the groundwater depletion all over the country. There are many areas where the ground depletion is very, very much happening. And also there is a problem of contamination, but that is you won't be able to do from this differential interferometrics are, but there can be linkage. If the aquifer compaction happen, there may be this contamination, this potential can increase. Okay, so that way it can be used as an input, but directly you cannot say much. Okay. The next question is, how can students contribute to disaster mitigation research using satellite data at an early stage? So there are many ways to do that, particularly there are lists, in fact. Okay, so if you can do the monitoring, for example, a particular disaster related issues, whether it is due to landslide, okay, or due to your earthquake. Okay, so for example, if there are landslide scar identification, okay, and this validation, the students from the satellite image, you can identify this scar, and depending on your locality, you can check whether the scar is there or not, and you can put it in the portal. There is a portal. This Geological Survey of India is there using a portal. Okay, so where you can also put this photograph of this landslide, what is happening and the location, and then it can be used centrally by your researchers, and you can also access to what others have collected. Okay, this way the crowdsourcing, so one can collect the data and you can put in the portal, and that portal can be used by many. Okay, that is one way. Also satellite image you can use. That's images from the Google Earth you can do, or many other ways. The satellite image Bhuvan, that ISRO web portal, where you can see these satellite images and many derived maps, and that you can analyze, and depending on your location, you can also see what is happening to that particular locality. And then last question from Vipul Verma: how does the inclusion of antecedent soil moisture change the reliability of rainfall threshold predicting landslide in different climatic conditions? It's a very good question, and this is related to our other expert. I don't know whether Dr. Chaturaj is there or not. Otherwise, I can explain to you. Not an issue. So I'm telling you. So what you are saying, the antecedent soil moisture condition is very, very important, because soil moisture conditions or antecedent rainfall, what is in the model it is used. But if you use the soil moisture condition, it is much more this your phenomena. It is much more proven, because if rainfall is there, that is one way of estimating the effect. What is the antecedent rainfall for last 7 days or last 50 days? But how it is going to this your affect this your soil in terms of this increasing this pore pressure of the material, that is can be directly observed from the soil moisture. So this how this climate change or the rainfall conditions is happening. So here with this antecedent rainfall, if you use the soil moisture as well, then this model can be further refined. So that way this rainfall induced landslide threshold modeling, this you can use this soil moisture condition of the antecedent soil moisture condition can be integrated with that, so that one can refine this your antecedent rainfall induced this landslide initiation. Okay. So there are very good questions from many of you, and you can come back to us. Many more questions to the faculty. There are 4 faculty I have told. Okay, you can write to the concerned faculty, or you can write to Dr. Chaturaj, your coordinator of the workshop, or to me. So we'll be happy to answer to the queries and questions. With this, thank you, and we conclude this workshop with this. Ashokji, it is fine. There is no more questions, I believe.
Yeah, no, sir.
Okay, so we can conclude now.
Yeah, yes, sir.
Okay, thank you. Thank you, all these members, Ashokji, Janardhanji, and all the faculty members and this GITDL team, Dr. Harish Karnatak, Mrs. Shefali Agarwal, Madam, our Dean IRS, Dean Academics, Dr. Pramod Kumar, and above all, Director IRS. His encouragement and his support, all this together, you could successfully conclude this workshop. And I think you have been benefited with this deliberations today. And if it is useful, you come back with your feedback. And if you have questions or queries, please write back to us. Thank you.
Thank you, sir.